Hello everyone, my name is Professor James Won-gi Hong and welcome to my lecture on Internet of Things, IoT. I'm a professor in the Department of Computer Science and Engineering at Pohang University of Science and Technology, POSTECH, located in Pohang, Korea. This lecture presents an introduction to IoT. I will briefly introduce myself and 4 industrial revolutions that are being mentioned a lot these days. I will introduce basic elements of IoT, its general architecture, and the technologies involved. I will present some examples or use cases of IoT that can help the audience to understand what IoT is all about. You can find useful references at the end that you can use to study further on IoT. Please allow me to introduce myself briefly. My education background since high school is from Canada. I joined POSTECH in 1995 as an assistant professor in the Department of Computer Science and Engineering. Since then, I had many interesting and valuable experiences, including co-founding a Silicon Valley startup in 2000 and working as CTO and Senior Executive Vice President of KT, Korea Telecom. So I have had many interesting and valuable experiences, and I'm here to share with you some of those experiences through the topic of Internet of Things. Before I talk about Internet of Things, let me talk about the 4 industrial revolutions. The core of the first industrial revolution, which started in the 18th century from Great Britain, was steam engines. These engines were powered by heating water by burning coal. This brought great efficiency in productions by changing manual productions to mechanical productions. The second industrial revolution came in the 19th century with the introduction of mass production assembly lines in Europe and America. It was possible through electricity, petroleum, and steel. Again, it resulted in ever greater efficiency and mass production. The third industrial revolution came in the 20th century with the development of electronics and information technology. The key aspect of this revolution is the automated production, requiring less human labor and increasing productivity even higher. Since a few years ago, we are considered to be in the era of 4th industrial revolution. The core of the 4th industrial revolution is the convergence of information and communications technology, ICT, incorporated with the Internet of Things, which is the topic of this course, artificial intelligence, AI, and big data analytics. IoT, AI, and big data have made intelligent productions. AI includes techniques and methods from machine learning, deep learning, computer vision, data mining, speech recognition, pattern recognition, and natural language processing. Now, let me introduce IoT. What is IoT? This is a sort of wiki definition of Internet of Things, or IoT. IoT is the internetworking of things embedded with software, sensors, and network connectivity, which enable these things to sense or collect data. And then these data are analyzed and then make some intelligent decisions. IoT allows things to monitor various objects, including human, animals, or some environmental conditions. It also allows things to be controlled remotely, providing convenience and improved efficiency. Things in IoT can be just about anything, including temperature, sensors, smartphones, CCTV cameras on the road, buses, trains, planes, and almost anything that we can think of. According to a survey done by Cisco, which is a global networking solution company, the number of things using IoT technology will increase from 14.4 billion devices in 2014 to 50.1 billion devices by year 2020. IDC, a US market research company, has predicted the global IoT market will grow from $1.9 trillion in 2013 to $7.1 trillion by year 2020. So in a nutshell, there will be an incredible number of things, and the IoT market will be very big. So if you're working in this area, well, you could be making lots of money. Now, let's look at some IoT services. At the bottom are the things or sensing devices, including home appliances, door locks, smoke detectors, and smartwatches. Then there are gateway devices or intermediate devices that exchange data with sensor devices and provide data to big data analytics servers in the data centers, which are then used by various IoT services, including home automation, health services, energy management services, and emergency services. Basically, all of these IoT services have a similar architecture. On the far left side of the slide, we have IoT endpoints, which are sensors, actuators, and aggregators. Sensors are devices that sense data. Actuators perform some actions, such as setting temperatures, shutting off switches, turning on lights, and so on. Aggregators aggregate data from sensors and send collected data to gateways. Then we have IoT infrastructure consisting of IoT routers or gateways. They interconnect with internet infrastructure to exchange data between the IoT devices and servers in the data centers. In the cloud or data centers, we have servers performing various actions related to data analytics. End user applications through smart mobile devices or PCs utilize these analyzed data. The human users may make some control actions through these client devices to perform some actions through actuators, such as making temperature settings on thermometers. Global cloud service providers such as Microsoft, Amazon, Google, and others have developed specialized cloud platforms called Cloud for IoT or IoT Cloud. They are basically providing the computing and storage services which are part of their cloud computing services. Plus, they are providing some sort of data analytics services for IoT. They typically collect data from sensors or gateways, perform various analysis, and make some actions and/or store the results for later use. Microsoft Azure IoT Suite, Amazon Web Services IoT, IBM Watson IoT, Google Cloud Platform, and Samsung Arctic Cloud are examples of these. There are many communications technologies used in IoT. They are mostly wireless networking technologies, personal area networks, PAN, technologies are used to exchange data in very short distances. Bluetooth, Zigbee, Z-Wave, NFC, RFID are major examples of personal area networks. Most of us are very familiar with Bluetooth, which is used to communicate devices such as wireless speakers, microphones with our smartphones. NFC, or near field communication, is a technology also used to open doors and make payments using our smartphones. Wi-Fi and PLC, power line communications, are examples of local area networks. PLC uses part of our electricity network bandwidth to transfer data. We're very familiar with Wi-Fi as we use quite frequently to connect to the internet from our smartphones or laptops. Mobile wireless networks such as 2G, 3G, LTE, mobile WiMAX can be used to exchange data between devices and gateways. LoRa, NB-IoT, Sigfox are mobile wireless networks that have been developed recently specifically for IoT. Telcos have begun to deploy these IoT networks nationwide around the world. In Korea, SK Telecom has deployed LoRa, and KT and LG Plus are deploying NB-IoT. There have been numerous industry forums that have been trying to standardize communication protocols among the devices in IoT. Many have merged and disappeared. As of this lecture, two dominant industry standard forums exist. They are OCF, Open Connectivity Foundation, and 1M2M. OCF focuses on interoperability of home appliances. Until 2016, there were two separate groups, one led by Samsung and another led by LG. Until now, when we have appliances, for example, TV and refrigerator from Samsung, and some others, such as washer, microwave, dishwasher from LG, these devices do not talk to each other. That means one could not monitor or control these appliances from a single mobile application. Now, they will be changing. At the end of 2016, those two separate industry forums have merged into a single industry standard forum called OCF. They are expected to demonstrate interoperability of appliances from Samsung and LG in the fall of 2017. Another famous IoT standard organization is called 1M2M, which is driven by telcos and telecommunication solution vendors from around the world. It tries to standardize cellular communications and related technologies for telco-related IoT applications. There are a few terms that are similar to IoT. USN, Ubiquitous Sensor Networks, has been around for more than 10 years. M2M, machine-to-machine, has also been around for a similar length. Recently, IoE, Internet of Things, or Internet of Everything, Cloud of Things, Web of Things are also being used. Although the terminologies are slightly different, you can think of them as same. They all try to achieve what IoT is trying to do. Hello everyone, this is Professor James Won-gi Hong from the Department of Computer Science and Engineering at Pohang University of Science and Technology, POSTECH. In this lecture, I will introduce the networking technologies used in IoT. I would like to thank Professor Youngju Seo, who is an expert in wireless and mobile networking in the same department, for helping me making the lecture slides on this topic. In this lecture, I will introduce key networking technologies used in Internet of Things. I will first compare the wired and wireless networks. I will then explain the most widely used wireless networks, namely cellular networks, Wi-Fi, Zigbee, Bluetooth, RFID, and NFC, near-field communication. The networks are largely divided into wired and wireless. In a wired network, devices are connected to wires and are fixed. That is, the devices usually do not move. An IP camera connected to Ethernet network would be a good example. In a wireless network, devices are not connected to any wires, but they communicate using wireless networking technologies. They typically are mobile devices, such as our smartphones and smartwatches. Wi-Fi, Bluetooth, and Zigbee are examples of wireless networks. Although most IoT devices may be installed and are not mobile because they have limited resources, using wired network for communication may not be suitable. Rather, light wireless networking technologies are more suitable for IoT communications. Therefore, we will focus more on wireless networks in this lecture. We can classify wireless networks differently, but a common way to classify them are according to the distance coverage. The coverage can be identified by the extent to which the base station can send signals and communicate. As for the smallest coverage, it can communicate approximately up to 10 meters. And we call it personal area network. When it is wireless, we call it wireless personal area network, or WPAN. WPAN has various wireless communications technologies such as Bluetooth, Zigbee, and NFC. For a slightly broader coverage, you can use a wireless local area network, or wireless LAN. Wi-Fi is the most widely used wireless LAN technology, with a coverage of approximately up to 100 meters. The IEEE 802.11 has defined a number of Wi-Fi standards over the years. Compared to the first one developed in 1997, the coverage and bandwidth have increased considerably. IEEE 802.16, or WiMAX, is a networking technology for wireless metropolitan area network, WMAN. It typically covers up to a few kilometers. Its coverage is wider than wireless LAN, but narrower coverage than cellular networks. In early 2000s, KT and SKT have deployed the Korean version of WiMAX called Wibro. It was a competing technology against LTE, long-term evolution. Unfortunately, LTE won the war, and Wibro is not being used that much anymore. It is being used to provide uplink communications in buses and taxis. The last one is called Wireless Wide Area Network, or WWAN, and cellular networks such as 2G, 3G, 4G, and 5G networks are examples of wireless WAN. These are the communication technologies that our mobile phones use to do voice as well as data communications. Now, I'll briefly introduce cellular networks. As you may already know, the cellular networks have gone through several generations. First generation, 1G, second, 2G, third, 3G, and fourth generation, 4G. Now, it is time for preparing the fifth generation, 5G, of cellular networks. So the LTE phone that you're using now is a 4G phone. Looking at the history of cellular phones, the first generation phone was analog and circuit switching was used with only voice communication possible. The main change in the second generation was a change to digital signals used instead of analog signals. Changing the analog to digital has a significant meaning. So the digital communication has begun from here. In 3G, problems arose when an optimized network of telephone lines called circuit switching is used for data communications, in addition to voice. In this way, there was a lot of waste. So it can be changed to the data packet switching way to be optimized for data rather than circuit switched, naturally optimized for voice as the data traffic increased. So packet switching was used instead of circuit switching in 3G. And we can say that it could be a real digital generation from second generation. And it was all digital after second generation, but it has been used in the packet switched way, away from the third generation. The packet switched is a form of data communication that is increasingly evolving in a packet switched way, as there are increasingly applications sending and receiving data rather than voice. This is also true for the wired network. In a wired network, the public switched telephone network was gradually replaced by the data network. The wireless has also evolved like this way as well. Now, as we are living in the 4G era, known as LTE or LTE Advanced, the difference between the third generation and the fourth generation is that the data speed is greatly improved. If you look at the pictures at the time, you can see that it shows that the phone was evolved in the first generation. The first generation phones were bigger tremendously to the radius in size. Now a very small and smartphone is being used. Then, as you can see on the right, smart pads are also used. They are optimized for data rather than voice, like smart pads on the right. 5G is being standardized and developed. The first implementation of 5G will be demonstrated by Korea Telecom at 2018 Pyeongchang Winter Olympic Games in Korea. Now I'll give you a more detailed explanation on Wi-Fi IEEE 802.11 standards. Wi-Fi is the most popular wireless LAN technology used by devices that people use, such as smartphones, smart pads, laptops. As I mentioned before, Wi-Fi is used for short-range local communication, such as at home, in schools, offices, cafes, train stations, airports, etc. Wi-Fi can be privately purchased and installed in private homes and buildings, but they can also be provided in public places by telcos. Example, KT, SKT, LG Plus in Korea. Wi-Fi operates on unlicensed bands called ISM bands. The industrial, scientific, and medical ISM radio bands are radio bands or portions of the radio spectrum reserved internationally for the use of radio frequency energy for industrial, scientific, and medical purposes other than telecommunications. Unlicensed bands mean those bands can be used by any device for any application legally. Licensed bands, for those bands that are sold by the government, typically to telcos for specific communication purposes, 2G, 3G, 4G, cellular communications, for example. Telcos pay a lot of money, more than $1 billion for a band, for example, so that they can use that band to do the business, that is, provide communication services, without any interference. Like I said, Wi-Fi networks use unlicensed bands. 2.4 gigahertz band and 5G gigahertz band are popular ISM bands that are used by Wi-Fi. There are two modes of operation for Wi-Fi: an infrastructure network mode and ad hoc network mode. I will explain more about these in the next page. The infrastructure mode is the mode that is most familiar to you. A Wi-Fi access point is called a base station. After buying an Wi-Fi wireless LAN hub or base station, you can connect the base station to internet by connecting it to a communication port in your home router provided by an internet service provider such as KT, LG Plus, or SK Broadband in Korea. In other words, you can think of the infrastructure mode as the base station. Even if there are hundreds of terminals under the same base station, they cannot communicate with each other directly, but only through the base station. The base station is connected to the internet. We call this the infrastructure mode. You can understand the notion that it's connected to communication infrastructure, and it is used as it is. We call that mode on the right as ad hoc mode. There is no base station here, so because there is no such controller, terminals need to communicate directly with each other. However, it should be within the communication distance. If it is too far away, obviously communication will not be possible. So the difference between the infrastructure and the ad hoc mode is that there is a one hop to go to the wired network in the infrastructure mode, but maybe many hops in the ad hoc mode. When it comes to the hop, we call it as a hop when we count how many devices you need to connect wirelessly. Since only the terminal and the base station are connected with wireless, it's called a single hop. Look at the right side. When a terminal communicates with other terminals, there might be a case that you have to communicate through several hops. This is called a multi-hop communication. I will give you more detail in the next page. As illustrated in the diagram, Wi-Fi mostly operates using an infrastructure mode. Like I have previously explained about the infrastructure network mode, there is a base station and the terminals communicate each other through a base station. When you configure your wireless access device, you notice a field called Service Set ID or SSID. You must configure all connecting devices and access points in a service set to use the same SSID. The two types of services sets are Basic Service Set, BSS, and Extended Service Set, ESS. A BSS consists of a group of terminal devices and one access point, which links to a wired local area network. An ESS consists of more than one AP. And ESS lets mobile users roam anywhere within the area covered by multiple APs. A BSS is connected to the wired network called the distribution system through the AP. And we call the connecting network in this way as the infrastructure network. As you can see here, wireless devices in ad hoc network mode are communicating with each other without a base station. For example, if we enter a war or went to North Korea, for example, then we will not have an infrastructure network that we can use. In that case, you will have to use an ad hoc network. If you need to communicate among the wireless devices that soldiers use, for example. So, the way that terminals communicate with each other without having a central base station is called ad hoc network. There are two BSSs in this slide. An independent BSS, IBSS, is an ad hoc network that contains no access points, which means they cannot connect to any other basic service set. That is, devices in IBSS1 and devices in IBSS2 cannot communicate with each other. Let me explain the basic process of Wi-Fi operation. Actually, it is fairly simple. It usually takes several steps. You can turn the Wi-Fi interface on and off in your smartphone while sliding down the setting screen. If you turn it on, the Wi-Fi interface will start searching for a base station. These days, you will typically find many base stations wherever you go, as illustrated in an image on the right. It is the unique name of the base station called BSSID, which I explained earlier. By the way, if the base stations use the same radio frequencies, naturally the interference will occur, right? No doubt. For example, if you turn on several radios at the same time, you will not be able to hear any sound properly. So the base station do not use the same frequency. It divides into things called channels to use differently. Just as we have TV channels, and they are different. Wi-Fi is divided into channels by setting slightly different frequencies. You might not know which channel having to use if you turn on the Wi-Fi interface card on your smartphone first. You will start to search a channel because you don't know which base station would be used for that channel. In this case, we call it channel scanning. So we will get information such as what base station it is, or about the signal intensity, and so on, while we are looking up for one by one. This is called beacon. Beacon frame is one of the management frames in IEEE 802.11 based wireless LANs. It contains all the information about the network. Beacon frames are transferred or transmitted periodically to announce the presence of a wireless LAN. Beacon frames are transmitted by the access point in an infrastructure basic service set, or BSS. A Wi-Fi device can use one of two ways to scan available channels: active and passive. During an active scan, the client radio transmits a probe request and listens for a probe response from an AP. With a passive scan, the client radio listens to each channel for beacons sent periodically by an access point. Base stations send a signal called beacon at regular time intervals. This beacon contains useful information about the base station, such as timestamp, beacon interval, SSID, the channel number, and capability information, and so on. You could get this information. After finding and selecting an access point, I wish to communicate with the next step required is authentication and association. Authentication involves checking whether the mobile device has the right to use the base station or not. Password checking is the most popular method of authentication. Once the authentication is performed successfully, the final procedure is the association. Mobile devices can associate or register with an AP or router to gain full access to the network. Association allows the AP to record each mobile device so that frames are properly delivered. Association only occurs on wireless infrastructure networks, not in ad hoc mode. A station can only associate with one AP at a time. After this, data transfer can happen. There are many Wi-Fi APs on the market today. In fact, various APs use different Wi-Fi standards. I told you that 802.11 is a set of Wi-Fi standards. Because there are many standards people have added alphabet letter after 11 to distinguish them. When the standard first came out in 1997, it did not have a suffix of alphabet after the standard number. People call it the 802.11 legacy standard. Then came B and A and G were added. Next, N was added. Recently, AC has been added. Other standards are still being developed. The difference is that the ISM band has two bands I mentioned earlier. The first one used 2.4 gigahertz without using 5 gigahertz because people wanted to use 5 gigahertz as well. Thus, the products that use 5 gigahertz band became available. ODFM is used as a transmission method in IEEE 802.11 N, and AC. OFDM is a frequency division multiplexing scheme used as a digital multi-carrier modulation method. A large number of closely spaced orthogonal subcarrier signals are used to carry data on several parallel data streams or channels. The antennas are divided into SISO and MIMO, depending on whether one antenna or multiple antennas is used. Therefore, if the device has more antennas, it will be able to send data further distance, and data transmission speed will get faster. Consequently, the process of sending more data in less time by combining various antenna technologies and transmission technology is a parameter of the channel bandwidth. As you can see, the alphabet letter became to use letter of alphabet, such as it goes to A, G, N, and AC. That means you can send more data at the same time. So if you look at the maximum transmission rate on the bottom of the slide, you can see that there is a huge difference. IEEE 802.11n is probably the most widely used product because several years ago, 802.11 AC became a standard. Most of the latest smartphones or Wi-Fi products that are being released today include the 802.11 AC technology. But 802.11n is still being used a lot these days. The difference is that how much data will be sent in a shorter time. Next, I will talk about wireless personal area networks. The first one is Zigbee. Zigbee is an IEEE 802.15.4 based specification for a suite of high-level communication protocols used to create personal area networks, or PAN, with small, low-power digital radios, such as for home automation, medical device data collection, and other low-power, low-bandwidth applications. Its low-power consumption limits transmission distance to 10 or 100 meters line of sight, depending on power output and environmental characteristics. Zigbee technology is used at home for lighting, switches, and temperature control devices. Zigbee operates in the ISM radio bands. 2.4 gigahertz in most jurisdictions worldwide, 868 megahertz in Europe, and 915 megahertz in US and Australia. Data rates vary from 20 kilobits per second for using 868 megahertz band to 250 kilobits per second for 2.4 gigahertz band. The Zigbee network layer natively supports both star and tree networks and generic mesh networking. Every network must have an coordinator device tasked with its creation, the control of its parameters, and basic maintenance. Within star networks, the coordinator must be the central node. Both trees, meshes allow the use of Zigbee routers to extend communication at the network level. Zigbee LightLink gives the lighting industry a global standard for interoperable and very easy to use consumer lighting and control products. It allows consumers to gain wireless control over all their LED fixtures, light bulbs, timers, remotes, and switches. Leading home lighting solution manufacturers, including GE, Greenwave, Osram, Sylvania, and Philips, have contributed their expertise to the development of Zigbee LightLink. It can cover the distance up to 70 meters indoors and 400 meters outdoors. Bluetooth is a wireless communication standard for exchanging data over short distances using short wavelength UHF radio waves in the ISM band from 2.4 to 2.485 gigahertz from fixed and mobile devices and building personal area networks, PANs or PANs. It is invented by telecom vendor Ericsson in 1994. Bluetooth is managed by the Bluetooth Special Interest Groups, or SIG, which has more than 30,000 member companies in the areas of telecommunication, computing, networking, and consumer electronics. The IEEE standardized Bluetooth as IEEE 802.15.1 standard, but no longer maintains the standard. The Bluetooth SIG oversees development of the specification and manages the qualification program. A manufacturer must meet Bluetooth SIG standards to market it as a Bluetooth device. Many versions of Bluetooth exist since the first version came out about 20 years ago. Bluetooth 1.1 and what we call BLE, or Bluetooth Low Energy, are the most important versions of Bluetooth. New products are coming out by new standards like Wi-Fi. Looking at the difference, naturally, the transmission speed is constant or getting better. What matters the most is the power consumption. As I mentioned earlier in this course, the power is an extremely important parameter in wireless communication products. It is directly related to the battery consumption in the product. Bluetooth Low Energy, or BLE, is a technology that dramatically reduced power consumption. The initial coverage was about 100 meters, but it was reduced to 50 meters in BLE version. You have to have a lower coverage if you want to reduce power consumption. This ensures a short transmission distance and a constant transmission speed. The released products that follow it can now be directly connected to the internet. They can have IP address through IPv6. The Bluetooth SIG officially unveiled Bluetooth 5 on June 16 in 2016. Its new features are mainly focused on emerging Internet of Things technology. The Samsung Galaxy S8 launched with Bluetooth 5 support in April 2017. Bluetooth 5 provides double the speed, 2 megabps, fourfold the range, and eightfold the data broadcasting capacity of transmissions compared to BLE. Bluetooth beacons are hardware transmitters, a class of Bluetooth low energy devices that broadcast their identifier to nearby portable electronic devices. The technology enables smartphones, tablets, and other devices to perform actions when in close proximity to a beacon. In Wi-Fi section, I mentioned that base stations send out beacons regularly. Similarly, these small BLE devices broadcast small messages to nearby devices. It's a small blue device attached on the wall as shown on the figure on the left side. Apple version of BLE beacon is called iBeacon. Let me explain the examples first. If you look at the first picture on the left, a BLE beacon in blue is equipped on the pillar at the entrance of a store, in a department store. This device periodically broadcasts beacon signal. If a lady with a BLE-enabled application running on her smartphone passes by this store, the app on her smartphone will receive this signal and act upon it. She may receive an information such as lady shoes are off 30%, or here's a 20% discount coupon that you can use in our store, etc. If you look at the example on the right, it shows an example of utilizing the beacon in a hospital. If a person went to the hospital and he or she could not find where he is at this time, Beacon will be able to help lost people find the direction they want to go. So when you cannot find where you are or where you are going in the hospital, it can help you find the place. So as I mentioned before, BLE Beacon is a product reducing its battery consumption. Accordingly, the battery life is typically 2 to 5 years. There's a fairly large deviation. The deviation depends on how far the signal will go. Of course, it can be set. So the other name is a nickname Bluetooth 4.0 or Bluetooth Smart. There are many other applications for this. Here I'll explain the principle behind BLE Beacon. As I mentioned before, BLE Beacon regularly broadcasts beacon signals, including UUID, to nearby distances. The UUID, or Universally Unique Identifier, and several bytes are sent with it, can be used to determine the device's physical location, track customers, or trigger a location-based action on the device, such as a check-in on social media or a push notification. As illustrated on the diagram, BLE Beacon transmits a beacon to a nearby device, and an app in that device receives it, and then it sends a request to a server, which in turn will provide some info from the content database, such as discount coupon for a store near the device. Next, I will present another popular wireless PAN technology called radio frequency identification, or RFID. RFID uses electromagnetic fields to automatically identify and track small tags attached to objects. The tags contain electronically stored information. Passive tags collect energy from a nearby RFID reader. It's interrogating radio waves, and the data stored in the tag is transferred to the reader. Active tags have a local power source, such as a battery, and may operate at hundreds of meters from the RFID reader for communication. A battery-assisted passive, or BAP, or semi-passive tag has a small battery on board and is activated when in the presence of an RFID reader. Unlike a barcode, the tag did not be within the line of sight of the reader, so it may be embedded in the tracked object. RFID is now used in many applications. RFID tags are used in many industries. For example, an RFID tag attached to an automobile during production can be used to track its progress through the assembly line. RFID tagged objects and products can be tracked through libraries, supermarkets, and warehouses. And implanting RFID microchips in livestock and pets allow for positive identification of animals. Next, I will explain NFC, Near Field Communication. NFC enables two electronic devices, one of which is usually a portable device, such as a smartphone, to establish communication by bringing them within 4 centimeters of each other. It is usually used in applications exchanging small amounts of data, such as IDs, payment amounts. It can be used for identification, attendance checking, opening doors, secure PC login, credit card payments, loyalty and memberships, entertainment ticketing, and so on. As you can see in the picture, the principle is that when two devices touch, the initiation device generates radio frequency field that transmits data to the receiving device. A smartphone being used to make mobile payments to a payment device is a good example. Let's summarize this lecture on networking technologies for IoT. In this lecture, I have explained the differences between wired and wireless networks. Wireless networking technologies, especially the wireless PANs, are the most suitable for IoT applications. Cellular networks, 1, 2, 3, 4, 5G, were presented. Of course, 3 and 4G are currently used in many IoT applications. Wi-Fi is used in smartphones and smart pads and other devices that are used to collect data and act as a gateway to the server or cloud in various IoT applications. Zigbee, Bluetooth, and RFID, and NFC are popular wireless personal area networks that are used in various IoT applications. Here are the references that you can look up for more detailed studying. Now, let me wrap up my lecture today. To summarize the flow briefly, numerous sensors generate various data. And the generated data is transmitted to the cloud by various network technologies. The data collected in that cloud is called big data. Intelligent IoT service will need to be provided when the big data is processing and AI technology is combined. Okay, that's it for today, folks. Let me call it a day, shall we? I hope my lecture today will help you understand networking technologies for IoT. Thank you. Hi, everyone. In this lecture, I would like to introduce how to set up and use Arduino yourself. Before we get started, here are a few things you need. You need a PC, such as a laptop or desktop, and a PC Arduino connecting cable with USB-A type on one end and USB-B type on the other end. Of course, we need an Arduino board. We will use the Arduino Uno version in this lecture, and we'll also need some options such as LEDs, sensors, jumper cables, and a breadboard in order to do various experiments. Here are the 6 steps you need to follow. First, you have to download and install the IDE software on your PC. You will then connect the Arduino board to the PC. Then launch the Arduino IDE. You can find and select the connected board and serial communications port. Once you have done this, you can write code for the program using the IDE and compile the code. You can then upload it to the board so that the Arduino board can do whatever it is supposed to do. Let me explain each process in more detail in the next few slides. First, download the IDE software from the URL provided at the Arduino official homepage. If you access the official homepage of Arduino, you can download the appropriate IDE for your PC operating system. Windows, Mac OS, and Linux versions of IDE are available. Please note that Arduino Web Editor is also available. You can write the code on the web and store your code in the cloud. You can start the installation of IDE when the download is complete. The installation process is not that difficult at all. When you start the installation, it will first extract the files in the installation package. This will take a few minutes. It then asks for your agreement on the use of the software. When you click I agree, it goes to the next step. It then asks you to select the component to install. Normally, you would not make any changes, but just click Next. When it asks you to select a directory to install the IDE software, unless you have very specific directory in mind, you would also just click Install button. It will then install the software on your PC. After the installation is finished, you can see that there is a shortcut icon created on your desktop. When you complete the installation of IDE software on your PC, it is time to connect the Arduino Uno to your PC. You should have prepared a PC Arduino connecting cable with a USB A type on one end and USB B type on the other end. In the cable, please connect the end of the USB A type to the PC and the end of USB type B to the Arduino board. When your PC and the board are connected, they are now ready to communicate. Of course, you will need to connect power source to the board as well. Now let's start the Arduino IDE software on your PC. The usage of IDE is very simple. You write your code in the code area and going through compiling and uploading it. Programs written using Arduino software are called sketches. These sketches are written in the text editor and are saved with the extension .ino. The editor has features for cutting, pasting, and searching, replacing text. You can create a new sketch or open an existing sketch by pressing the New or Open button respectively. After editing, you can save the sketch you edited by pressing Save button. Then you have to press Verify button to compile the sketch. Then you click the Upload button to upload the program to your board. And then you can check to see if serial communication is working well by opening the serial monitor in IDE. What you need to do in the IDE is to make sure whether your PC has a good connection to the Arduino board. If you go to the tool in the menu bar, you can select Board. You must select the correct version of the Arduino board that is currently connected to the USB cable. Subsequently, you should also check the serial port on your PC. You should check to see whether which communications port is currently connected to the Arduino board. In order for Arduino board and IDE to communicate normally in this way, check the Arduino board version and make sure that the port number is correct. Once all the settings are complete, it is time to write the code. As I mentioned earlier, a sketch is the unit of code that is uploaded to and run on an Arduino board. By writing this sketch, the program can be completed to be uploaded to the Arduino board. The sketch should basically have two types of functions. One is called setup function, and the other is loop function. The setup function is called when a sketch starts. Use it to initialize variables, pin modes, start using libraries, etc. The setup function will only run once after each power-up and reset of the board. After creating a setup function, which initializes and sets the values, the loop function does precisely what the name suggests and loops continuously. Here is where the main code should go. It is used to actively control the Arduino board. Arduino program language, which is based on wiring, is used to write the code. If you have any difficulties writing a sketch or you don't know how to use it, there is a reference you can look up. If you go to Help on the menu bar, there is reference where you can find information about the structure of sketch, how to use various variables and basic functions. After completing to write a sketch, you'll need to go through the verify process to check whether the code has any bugs or problems. You can easily compile the code by pressing the Verify button at the far left. If the compiling is completed successfully, you can see Compile Completed in the message window at the bottom of IDE. But if there is an error in the code, an appropriate message will be displayed on the message window. After the compilation is completed, without any errors, you can now upload the program to the Arduino board. The Arduino board will run according to your program. If you have written a program to measure temperature and humidity, the Arduino board will continue to measure temperature and humidity until the power is turned off. Once the uploading is complete, you will need to check whether the Arduino board is working properly. If it works fine, it does not matter, but if it does not work as intended, it'll be necessary to check if the program you have written is correct or the circuit configuration is correct. Well, in this lecture, I have explained how to set up and use Arduino. In the next lesson, we will walk through the tutorials with some basic examples. See you soon. Well, after listening to my lecture, if you're still not quite sure how to use your board, then you can watch some of these videos. They will help you understand better on how to get started with your Arduino board. Hi everyone. In this lecture, I will give a first tutorial on Arduino. I will explain how to turn on and off the LED, which is built in on an Arduino Uno board. As you already know, Arduino board has basic LED mounted for testing purposes. The position is located to the left of the Arduino's mark. This LED is internally connected to digital pin number 13. So inputting the digital pin number 13 to a 5-volt output, the LED will be turned on. So I'll show you how to turn this built-in LED on and off in this tutorial. Let's start with a sketch that makes the LED circuit connected to digital pin number 13 turn on. First, your sketch has to tell the Arduino to set the direction of pin number 13 to output using the pin mode function. The pin parameter is the number of our digital I/O pin, which is 13 in this case. And mode must be either input or output. Since we're going to turn on the LED, pin mode will be set to output. Since we're going to turn on the LED, pin mode will be set to output on pin number 13. Thus, write pin mode 13 output. You should always use a semicolon at the end of the command. Now that digital pin number 13 is set to output, we can use digital write to turn the LED light on. Digital write 13 high makes the Arduino microcontroller connect digital pin number 13 to turn on the LED. After creating the sketch like this and going through compiling and uploading it, you can see that the Arduino board LED is turned on. Now, I'll show you how to turn this built-in LED off. The command to turn off the LED is very easy. In the sketch of turning on the LED used above, you just change the high in the digital write to low. That turns off the LED. If you modify the sketch and do compiling on uploading it, you can see that the LED is off as shown in the figure. In this tutorial, I explained how to turn the LED on and off as the first tutorial on Arduino. You can write a program that blinks while the LED turns on and off by applying what you learned today. Can you write a program that LED flashes on and off once every second? Now, I'll give you IoT use cases or examples so you can understand what IoT is all about. The first IoT use case is smart thermostat. This IoT application is quite simple, but it is one of the early IoT applications that surprised the world by Google acquiring this small startup company called Nest for $3.2 billion in January 2014. It showed a big potential for IoT applications. Nest Learning Thermostat learns the behavior of users, intelligently controls heating and cooling, and saves energy and money. The second use case is smart healthcare. Smart sensors are attached on our shoes, wrists, and other parts of our body to monitor our activities and health conditions. The data are recorded on our smartphones and then later transferred to big data and analytics engines in the servers in the cloud for detailed analysis or trend analysis. These devices act as sensors to monitor our health status. The third IoT use case is wearable devices. Smart electronic devices can be worn on our body, such as smartwatches, smart bands, or glasses. They provide simple information such as time of the day, how many steps or kilometers I have walked so far today. Most of these devices use Bluetooth technology to be paired with smartphones to upload monitored data. The next IoT use case is smart buses. The buses in our city are tracked using mobile wireless network technology and provide useful information to riders, such as when the next bus will arrive. Before this kind of IoT system, riders had no idea when the next bus will arrive at the bus station. The map on the left shows the map of Seoul, Korea. and its bus routes. Seoul Bus application can be downloaded for free, and then users can use the app to find out where the Seoul buses are, particularly the bus that they are interested in riding. The photo on the right bottom shows a bus information terminal displaying bus numbers and when they will arrive at the particular bus station. This diagram illustrates how the buses are tracked in the bus information system in Seoul. Each public transportation bus in Seoul has a GPS-enabled device with an mobile wireless communications uplink to the internet using 3G or LTE. The GPS data of each bus is transmitted to the Bus Information System, or BIS, center at some interval, at every 40 seconds, for example. The BIS predicts arrival time of next bus for each bus station and provides that info to Bus Information Terminal and other internet application systems, which in turn provide the same info to users through various applications. This IoT use case is Smart Subway. The left map shows a subway map of Seoul, which has about a dozen subway lines. The right image shows a subway app usage for going from Seoul train station to Gangnam subway station. It shows which subway line to take, where to transfer, and how long it takes. This IoT application works similar to how smart buses work. Subway trains are monitored by the central subway information system, which provides the location information to whichever application that wants to use. In this use case, subway trains are examples of things. This IoT use case is smart highways. The highways in Korea and many countries around the world have CCTV cameras installed, and traffic is monitored. The images shown on the slide are from a mobile app provided by the Ministry of Transportation. The left image shows the traffic condition of highways near Daejeon, a major city in the middle of the country. Green lines represent highways without much traffic. Yellow lines indicate slowdown of cars because of some traffic. And red lines indicate very slow roads due to heavy traffic. If possible, you can try to avoid the yellow or red colored areas of the highways. One can look at the live highway conditions using the live cam function on the right. Without such applications and information, drivers have no idea about the traffic conditions of the roads on the way to their destination. It is essential to use navigation device these days when we drive. Until a few years ago, we used a separate navigation device. These days, however, we have a number of smart navigation apps that provide useful navigation information that incorporates the current traffic condition of the roads. Thus, we can drive safely and smartly avoiding congested areas and arrive at the destination without delays. This is another very useful application of IoT. The cameras and sensors on the roads provide useful data on the current traffic condition to the central traffic information system, which in turn provide information to various applications that wish to use the data. Self-driving cars or smart cars is a hot use case of IoT these days. It is much more sophisticated than the previous IoT use cases introduced. Not only traditional mobile manufacturers such as Volvo, Hyundai, Toyota have been developing these, but also internet companies such as Google, Uber, Naver have also been developing self-driving cars. The next IoT use case is smart farm. Farms have been utilizing IoT technology to remotely and automatically manage the growth environment of crops and livestock. Farmers can control the devices such as mistifiers, water pumps, vents, heaters using their smartphones from anywhere. More intelligently, the environment can be monitored and these devices can be controlled automatically to provide a good condition for farming without the intervention of human. Here is a short news video clip describing a smart farm with IoT.
Smart farming technology is set to bring changes to Korean agriculture, which is struggling under the weight of an aging farming population amid rising imports. Pilot projects are underway at farms specializing in various crops with the goal of modifying the system for regional use. Our Park Se-young has the details.
At this tomato farm, the ventilation system is activated automatically when the humidity inside the greenhouse exceeds 80%. At night, a cover for ceiling and warmth unrolls on its own. The facility is making use of smart farm technology that enables customized control of greenhouses. The settings can be modified from anywhere using a computer or smartphone.
It reduces time and the inconvenience of travelling back and forth, and I worry less when I'm away because I can check on my farm anytime.
In 7 regions across the nation, farms that specialize in various crops tested the Smart Farm service as part of a year-long trial conducted by the Rural Development Administration. After the year was up, the farmers gathered to offer their feedback. 3 crops were harvested during the trial year. Chrysanthemum farmers reported a 10-day reduction in the number of days it took to get to harvest and energy savings of 35%. Grape farmers reported a reduction in grapeberry cracking from 12% to 5%. Despite the benefits, participants still thought the system could use some improvement, though the RDA vowed to address their needs.
After receiving feedback on site, we can make up for the drawbacks and develop manuals for autonomous distribution of the Korean model of the system.
The RDA is set to add 7 more farms specializing in different crops next year to polish the system for use in Korea. Park Se-young, Arirang News.
Another IoT use case is forest or mountain fire monitoring. IoT sensors are installed in various parts of the forest. When fires happen in forests and mountains, you need to detect them quickly and then send alarms to the fire departments so they can come and put out the fire. So more places are using these special sensors to sense the smokes and fire. It is very difficult to put out fires by firefighters in forest and mountain fires. These IoT sensors can provide useful information for the shortest path to the fire location as well as the direction of the fire spreading. It can also provide useful info for assisting people to evacuate to safe places rather than going to the direction of fire. Asset monitoring is very useful IoT application that can be enjoyed by not only companies but also by individuals. Small IoT sensors are attached on valuable things such as computers, printers, and other easily movable devices. Companies can discover where all of these devices are located very easily. When these devices go out of the range, for example, to outside of the property illegally, the monitoring system can generate alarms to warn the administrators of such an illegal event. We're now seeing some commercial applications of these small IoT sensors being attached to our wallets for tracking our wallets. We can find these wallets quickly when they are misplaced or stolen. Google, of course, has been working on these IoT applications. And let's see what Google has been doing by watching this video clip.
Good morning, Jillian. From 8 to 10 a.m., you have building shuts off the hot water.
Okay, Google, what are my reminders?
Your reminders for today are, ask Kelsey to prom.
Okay, Google, call 24/7 Lock Lads.
Okay, Google, call Kiss's Plumbing.
Call Lisa.
Calling Lisa.
Hey girl, where are you?
I'm coming. I just finished the cake.
No cake. She's gluten-free right now. Just make a fruit salad. They're festive.
What are we watching here, huh? Hey, Google, play the Warriors game.
All right, playing Warriors.
100-layer challenge complete. Dude, where's my phone? Hey, Google, call Danny.
Calling Danny.
Seriously, dude?
Okay, ready? First one to laugh loses. Okay, Google, show me funny videos on YouTube.
Here you go.
Play the fourth one.
Hey Google, play my dance playlist.
Playing now.
I got rockets in my shoes.
Hey Google, play my dance playlist.
I got a condo in Manhattan. Baby girl, what's happening? You and your ass invited. Lucky for you, that's what I like. That's what I like. Lucky for you, that's what I like. That's what I like.
This video clip is a promotion from AT&T, the biggest telco in the world, showing what people can do with the IoT services provided by AT&T.
We live in a world where machines are everywhere. They're local and global. And when connected to the Internet of Things, they can help transform your business. Today, building a successful IoT solution can be complex. Businesses must securely deploy the right sensors, devices, networks, and platforms. And without the right expertise, planning for all of it can be challenging. Which is why AT&T offers a complete suite of IoT solutions and services, so you can reduce development costs and increase your speed to market. Turning data into actionable information is more than just connecting devices. It takes end-to-end IT systems and services, including platforms designed to speed your development time, cloud-based data storage, and multi-layered security. With thousands of devices certified on our global network, we make it easy to choose the right device for your IoT application. So whether you're in transportation and connect via cellular with Global SIM, remote equipment using dual-mode satellite with cellular backup, or a smart city needing Wi-Fi hotspots or low-power options, we have you covered. AT&T, providing everything you need to adapt quickly and create brilliant machines. Giving you the agility you need to integrate and accelerate your business with the Internet of Things.
This video clip is a promotion from Rogers, one of the biggest telcos in Canada, showing what people can do with the IoT services provided by Rogers.
Have you ever stopped to think how the food on your table got there? From pick to pickup to keeping food fresh and reducing waste, how these strawberries traveled from a farmer's field to here is an interesting story. Behind the scenes, a lot of innovative technology helped make it happen. Little network sensors tracked, predicted, and controlled the journey to your plate. These capabilities are all part of the Internet of Things, or IoT, and they can deliver big results for Canadian businesses. Let's have a look. From the moment crops are planted, IoT technology is there to help the farm business flourish. When the berries hit the road, these little sensors can alert you to things that affect perishable food. In manufacturing, the same technology is ready to help you make the most of your processes, so you can remotely monitor, maintain, and automate equipment, appliances, and tanks. When it comes to a kitchen, sensors and software log temperatures and monitor equipment for you, helping reduce waste and maintain food safety. Now, we've been concentrating on strawberry production here, but the reality is IoT technology has the power to benefit businesses in any industry. In fact, it has already begun to transform Canadian businesses. That's how Rogers can help. As Canada's leading IoT provider, our turnkey solutions are ready to make it all happen with ease. We'll set up the technology and help you manage it, saving you both time and money. With us, IoT is a piece of cake, or pie. See how IoT solutions can turn little things into big opportunities. Get started with a complimentary IoT readiness assessment.
So far in this introductory lecture, I have explained how IoT is important in the fourth industrial revolution, what IoT is, and IoT use cases in our daily lives. I'm going to conclude this introductory lecture by mentioning the importance of security in IoT applications. This is an important area of research that can be done continuously as we develop more useful IoT applications. IoT can do many useful things for us. However, IoT security is an area that needs a lot of work. Since the characteristics of IoT is quite open and involves many different devices and communications, there can be many vulnerable places that hackers love to infiltrate. There are several examples of IoT hacking. The first example shows a hacker controlling someone's smart thermostat and asking for ransom money. The second example shows vulnerability of a vehicle. The third example shows the vulnerability of our road signs. This is my vision of IoT. IoT will make our lives more comfortable, more convenient, safer, more enjoyable, and healthier. IoT will also increase the productivity and efficiency in industry. I have taught this course on IoT twice in previous years at Post-Tech, the following is the IoT course website at Post-Tech. You're welcome to visit it and enjoy various useful info and video clips on IoT. This slide shows the topics that will be covered in this course. Following this introductory lecture, I will introduce networking technologies used in IoT applications. I will then introduce several popular IoT development kits and IoT programming using them, namely Raspberry Pi, Arduino, and Samsung Arctic IoT platform. I will introduce several IoT cloud platforms such as Microsoft Azure IoT Suite, Samsung Arctic Cloud, Amazon Web Services IoT, IBM Watson IoT, Google Cloud IoT. I will then introduce an IoT application development project that can be carried out throughout the course. The following 5 pages introduce topics that are used in this introductory lecture, and their references on the internet. You can use the references to study the topics further. I hope you will stay around for this term, learn a lot, and enjoy the course. Hello everyone, I'm Professor James Won-Gi-Hong from the Department of Computer Science and Engineering at Post-Tech. Today, I will introduce Arduino, which is probably the most popular IoT device development platform in the world. The table of contents for this lecture is as follows. First, I will introduce what Arduino is. I will then introduce various versions of Arduino boards, as well as add-ons that you can attach to the board to do various things. I will then briefly introduce some Arduino projects. So, what is Arduino? Well, Arduino is an open source electronics platform based on easy-to-use hardware and software. It is intended for anyone, beginners as well as experts, making interactive things. Arduino is the most popular IoT device development platform. Arduino can sense the environment by receiving inputs from various sensors and affect its surroundings by controlling lights, motors, and other actuators. Arduino consists of an Arduino board, hardware, plus IDE, software. Arduino board is a microcontroller board used to sense and actuate. IDE, Integrated Development Environment, is a software tool that helps you write, compile, upload code to the Arduino board. The core component of Arduino board is microcontroller. Well, what is a microcontroller? You can think of a small controller on a small chip. It contains a microprocessor, memory, such as RAM, ROM, flash memory, and various inputs and output ports as illustrated in the diagram on the left bottom of this slide. It is usually embedded in a device to control the device. It is used in many embedded systems such as smartphones, toys, household appliances, mobile platforms, automobiles, cameras, and so on. Companies such as Intel, ARM, Atmel, Samsung have been producing microcontrollers. Arduino programming language based on wiring is used to develop Arduino programs. In the next module, we will tell you more about this Arduino programming language. IDE is a cross-platform application development tool written in Java and includes a code editor with features such as cutting, pasting, searching, and replacing text. You can easily compile the code, upload the program to the board, and execute the program. We refer to this Arduino program developed using IDE as a sketch. To look at how Arduino works, first, you have to connect the Arduino board to your PC using a USB cable. This is needed for serial communication between the board and PC. USB A type is connected to PC, and USB B type is connected to the Arduino board. Now, you connect the sensors to the Arduino board. Then you create a sketch on your PC. You then compile the sketch and upload it to the board. When the program runs on the Arduino board, sensors can collect data and send it to the PC. Arduino is an open source hardware and software platform. Many of the projects made with Arduino board are open and well documented. That means you can utilize a lot of existing codes and extend them to suit your needs. The Arduino program language can be expanded through C++ libraries, and AVL codes can be added to your Arduino code. In addition to the Windows operating system, it also supports macOS and Linux. Arduino can easily connect digital as well as analog sensors and actuators. That is, it can easily connect temperature sensors, GPS locator sensors, accelerator sensors, and so on. It can also be connected to actuators such as LEDs, switches, and electrical motors. So, why should we use Arduino? Well, the answer is very simple. It is because of ease of use. The platform is easy to use, and the programming language that Arduino uses is very easy. It provides a simple structure and interface so that even beginners can learn quickly. As for the development environment of Arduino, the IDE is also very simple. In addition, you can easily find many information you need through YouTube videos, documents, and tutorials on the internet. This is because many people are already using it and sharing their experiences and codes. Many types of shields can be added. Arduino shields are modular circuit boards that piggyback onto the Arduino board to perform extra functionality. Typical examples are Ethernet shield and Wi-Fi shield. Let's not forget about the price is very cheap. Arduino board is somewhere between $30 to $40 each. I think most people should be able to afford this. And the price compared to performance is very good. Therefore, it is most widely used around the world. Now, let's look at various flavors of Arduino. There are many different versions of Arduino board available. They are largely divided depending on the number of input-output channels, the form factor, and the built-in processor. Uno, Leonardo, Do, Micro, Mini, and Nano, Lilypad, Esplora, and Mega are some of the available flavors. In the following slides, we will explain each board in more detail. The most popular version is Arduino Uno. In my opinion, this Arduino board is the best one to get started in developing an interactive thing. Many people are working on various projects using the Uno version, and it is the most well documented of the whole Arduino family. Basically, it has a size of 68.6 millimeter in width and 53.4 millimeter in length. And it is slightly larger than a credit card. It weighs 25 grams and it's very lightweight. The Uno version consists of microcontroller, 14 digital I/O pins, 6 analog inputs, a USB connection, and a power jack. Leonardo is a slightly upgraded version of Uno. It looks very similar to Uno, but has more than 20 digital I/O pins. And the biggest difference is that it allows users to do programming to control input devices like keyboard and mouse. And it has a built-in USB capability. Arduino Duo has a faster processor and a larger number of pins than Uno. Arduino Duo is the first Arduino board based on a 32-bit ARM core microcontroller. It has 54 digital I/O pins and is suitable for larger Arduino projects. Arduino Micro is a very small version, as its name suggests. In addition to Micro, other small-size versions such as Nano, Mini are also available. Micro version is the smallest board in the Arduino family. Because it has all the features of the Leonard version, we also call it a small version of Leonard. Arduino Lilliput is a version designed for wearable applications. It is used to add various effects or functions by attaching it to the clothes by using conductive thread and conductive fabric materials together. Arduino Esplora is also a derived version of Leonardo and used mainly for a game controller. It includes a joystick, slider, temperature sensor, accelerometer, microphone, and light sensor. It is designed for people who want to start a fun project about Arduino without having to learn electronics. Arduino Mega is the most powerful board, as the name suggests. It has 54 pins so that you can operate many communication pins. Further, it has a larger amount of memory so that it can be used for large, complex projects. There exist many boards similar to the Arduino board. Beagle board and Maple, made by Leaf Labs. Orange board, made by Korea's Cocoa Fab, are good examples of these. They are designed for use similar to the Arduino board, with some performance differences. The biggest difference between these and Arduino is that Arduino is an open source, but the others are not. In this section, I will explain Arduino add-ons, which are shields, modules, sensors, and actuators. There are shields, which are modules and actuators that are used to attach add-on to Arduino board. There are many kinds of Arduino shields. For example, GPS shield has a function to receive GPS location data. Power driver shield allows you to use a computer power supply for other power source. LCD shield serves as displaying information through the screen. Touch screen shield is a shield that provides touch screen capability. Data logging shield that can easily store and load data. Sound shield allows sound or music to be played. Communication shields are used to provide communication capability between the Arduino board and external entities, such as aggregators or gateways. Zigbee shield allows the Arduino board to communicate wirelessly using the Zigbee protocol. Ethernet shield allows wired communication using Ethernet. Wi-Fi shield enables wireless communications with Wi-Fi base stations and devices. Modules are functionally equivalent to shields. There exist various modules that can be added to the Arduino board. GPS module, Bluetooth module, RFID module are examples of modules. The modules can be connected to the board using jump cables. It does not sit on the Arduino board, and you can easily access other pins without any physical or electrical hindrance. However, a shield is something that sits on top of the Arduino board and literally shields it. The right bottom image illustrates an Zigbee shield sitting on top of an Arduino Uno board. The sensors that can be connected to the Arduino board as add-ons are really diverse. The gas sensor can be used to detect gas. You can also use an ultrasonic distance measuring sensor to measure the distance to an object. You can use the temperature and humidity sensor to measure the current temperature and humidity. You can measure the degree of bending or degree of curve using the flex sensor. You can also use the sound sensor to detect ambient sounds and measure their strength. The photoresistor is an illuminance sensor. It can change the value of resistance according to the amount of light. The brighter the surroundings, the higher the resistance value. On the contrary, the darker the surroundings, the lower the resistance. The force-sensitive sensor is a pressure sensor. It is used to measure how much pressure is currently being received. Piezo sensor is a vibration sensor. Hall effect sensor is a sensor whose voltage varies with the intensity of the magnetic field. Tilt sensor is a sensor that measures a tilt of object. When the tilt is detected, the circuit of the sensor flows electricity. Actuators can also be connected to Arduino. Actuators are used to perform some physical actions, such as turn on a switch, light, display info, and so on. The Arduino board receives data through the sensor, performs appropriate processing based on it, and gives commands to the actuator. LED is a physical actuator. It can be turned on or off. The LED according to the Arduino's command. Besides, it is also the actuator's role that enables the display to show on the LCD screen. It is also actuator's role that makes the sound from the speaker and turn the motor. In this section, we'll introduce some interesting Arduino projects. Well, there are many diverse and exciting projects that use Arduino, perhaps thousands of them. Rear Eye is an Arduino project that provides an additional eye. An ultrasonic distance measuring sensor is attached to the LilyPad version. If you're going around attaching it to your pocket or backpack, you can measure the distance to nearby objects in real time. Next is a camera that moves along the movement of surroundings. At the bottom, there are sensors placed in various directions to detect a movement by. These sensors capture the movement of nearby people or things and move cameras along the direction they move. Here are many other interesting and exciting projects. An LED matrix can turn on and off the LED to suit the mood and speed of the music. A flash control that turns on and off the LEDs of various colors. And there is a project like Google Earth Walk that can project a screen of Google Map onto the road floor and walking to find the way in person. These references can be used to find other interesting Arduino projects. Let me wrap up this lecture on Introduction to Arduino here. In the next lecture, I will introduce how to program Arduino boards to perform various interactions with sensors and actuators. Goodbye for now. Hi everyone. In this tutorial, we will learn how to blink the built-in LED and how to connect and control the external LEDs. At the end of the last tutorial, I asked you to think about how to write a sketch that blinks the built-in LED. This can be achieved by combining the two exercises shown in the previous tutorial. That is, combining the LED on and off steps with some delay in between. That's what we will do in this tutorial. Let's write the sketch. The built-in LED to be used in this exercise is internally connected to digital pin number 13. So you can turn on the LED if you make the digital pin number 13 to input 5 volts. So you have to set pin mode as number 13 and output. To turn on the LED, please use the high in digital write. And on the contrary to this, if you use low, the LED will be turned off. If you turn it on and then immediately turn it off, we cannot detect the blinking of the LED because Arduino is too fast to our eyes. The Arduino microcontroller uses a 16 megahertz clock. Therefore, only if turning it on and off with some time difference, we can see the blinking with our own eyes. The command to make time difference is delay. Delay in milliseconds is a command to make a delay before the next command by the number of milliseconds written in parentheses. The delay 1000 used here is 1000 milliseconds, which means the following command should be executed after 1 second of delay. Now, let's upload the sketch you made. You can see that the LED on the board blinks once a second, while the IDE displays the text upload completed. There are a few ways to stop it, but now you just unplug the USB cable. Once uploaded, the sketch is stored in the microcontroller unit forever until you upload a new sketch, which will cause the LED to blink wherever you power up. The second exercise in this tutorial is an exercise to control an external LED. The purpose of using Arduino is to control actuators such as LEDs or motors that are external to the Arduino board. So we need some preparations for this exercise. We will need 2 jumper cables. One will connect the digital pin number 2 on the Arduino board to the breadboard. And the other will connect the breadboard to ground on the Arduino board. Next, 1 LED is required. We have to pay attention to the polarity of the LED. The long side of LED wire is positive, and short side is negative. When we organize the circuit in this exercise, we will connect the long lead wire to the digital pin number 2 and the short lead wire to the resistor. And we need a resistor. This is to protect the LED. LED appears to the Arduino as a short circuit, since the resistance of an LED is nearly 0. The resistor and LED combination have some resistance, which, using the Ohm's law, allows you to calculate the current following through the LED and resistor. You need to size the resistor to limit the current to what the Arduino is capable of providing. The LED by itself will draw an infinite amount of current and damage the Arduino. Finally, we need a breadboard. The breadboard consists of power rails and terminal strips. Each power rail is horizontally connected internally. Conversely, each terminal strip is internally connected vertically. We can create a circuit to control an external LED on a breadboard, as shown on this slide. We need two jumper cables, LED resistor and breadboard. You connect the positive pole of the LED to pin number 2. Of the digital pin. On the contrary, the negative side will need to be connected to the 220 ohms register. And the other side of the resistor is connected to the ground pin. Of the Arduino board so that the current can flow. The resistors have no polarity, so you can connect them in any direction. The green line indicates the internal connection of the breadboard, and the holes on the green line are electrically connected. Therefore, you must configure the circuit to take into account the internal connections. Now, let's write the sketch for this circuit. The sketch is very similar to the sketch you did in the previous tutorial. First, you have to set the digital pin number 2 in setup function to output. And then you also set high in the digital write function, in the loop function. At this time, the LED will turn on. Next, set the delay to 500 milliseconds or 0.5 seconds and set low in the digital write function to turn off the LED. Because the loop function repeats over and over, the program will blink the LED every 0.5 seconds. So, now you compile the sketch you have written. When you're doing the compiling, it does not matter whether the computer and Arduino board are connected. However, when you are uploading the computer and the Arduino board must be connected to each other. If you upload to the Arduino board, you can see the external LED is blinking every 0.5 seconds. And this tutorial, we have been practicing the blinking of built-in LEDs and external LEDs, respectively. In the next tutorial, we will do an exercise to measure the amount of light. By the way, if you're not familiar with how to use a breadboard, take a look at the tutorial on how to use a breadboard, which is available on the given URL. The video on that website explains how to use it very well. You can learn how to use it in a few minutes. We will see you in the next tutorial. Bye for now. Hello everyone. In this tutorial, I'll go into the practice of measuring the brightness of light using Arduino. In this tutorial, we'll use an analog sensor. Analog and digital signals are used to transmit information, usually through electrical signals. In both of these technologies, the information, such as audio or video, is transformed into electrical signals. The difference between the analog and digital technologies is that in analog technology, information is translated into electrical pulses of continuous amplitude. In digital technology, the translation of information is done into binary format, that is 0 or 1, where each bit is representative of two discrete amplitudes. However, when we try to use the sensor plays a role to collect analog data around us. And then we can read them because it converts the analog data into digital data. The sensor we will use in this tutorial is a sensor called photoresistor. Another term for it is light dependent resistor, or LDR. The sensor is a sensor whose resistance value increases or decreases with the brightness or amount of light. So the circuit to be constructed in this tutorial has the following characteristics. The brightness of LED will be changed according to the brightness of the environment. If the surroundings are dark, the LED will also become darker. If the surroundings are brighter, then the LED light will also become brighter. The circuit configuration for measuring the brightness of light is shown on the slide. Compared to the last practical exercise, this is a bit more complex. We need to have two resistors, one 2K ohms and 220K ohms resistors. The circuit works as follows. First, a current begins to flow from the red power at the bottom of the Arduino board. The current goes through the photoresistor and the 2K ohm resistor to the ground on the Arduino board. And the measured amount of light is sent to the pin number 4, or A4. Then, according to the amount of light, the current flows from the digital pin number 10 with output mode and goes to the LED. Then at this time, it adjusts the LED brightness by the amount of light measured while passing through the LED. Let's write the sketch for the light measuring circuit. First, set the digital pin number 10 in the setup function to output mode. This is because the circuit is configured to turn on and adjust the LED on the digital pin number 10. Then we use the serial begin command. This is the stage to prepare for a serial communication. This is needed because serial communication is essential for a sensor to measure the amount of light and transmit data to the PC. 9600 means serial communication speed at 9600 bits per second. The serial communication is the process of sending data one bit at a time. Sequentially, if you use serial print, hello world, then you can print the text hello world to the serial console, or brightness equals in this example. However, serial begin 9600 does not actually print anything. Rather, it initializes a serial connection at 9600 bits per second. Both sides of the serial connection, that is the Arduino and your computer, need to be set to use the same serial connection speed. If there is a mismatch between what the two systems think the speed is, then the data will be garbled. So both the sending system and the receiving system need to agree on what speed to use. Next, let's look at the loop function. The Arduino command to read analog values is analog read. When you try to configure the circuit, you have to set analog read to A4 because the sensor is connected to the analog input A4 pin. And you have to make the digital pin number 10 to turn the LED on using the analog write command. It is different from digital write, which just has high for light on or low for light off. Analog write can be used to set the brightness of LED according to the brightness of the light in the environment. At this time, the reason why the value is divided by 4 is set is because the analog pin reads the value by using 10 bits. But the digital pin expresses the value by 8-bit. The number that can be represented by 10 bits is 1024, which is 2 to the power of 10. But the number that can be represented by 8 bits is 256, which is 4 times the difference of 2 to the power of 8. Therefore, the data value read from the analog pin is divided by 4 and used as a digital value. Here we show how to display the measured values for easy viewing through the monitor to see how much brightness is being measured. This can be done using serial print and serial print line function. Then we have to set the delay to make the measurement every 10 milliseconds. After we complete writing the sketch, we need to compile and upload it to Arduino board. This slide shows measuring the brightness of the light and outputting the result to the serial monitor continuously. At this time, if you shine a flashlight on the sensor, you can see that LED brightness and serial monitor value change. Conversely, let's try to screen the sensor with your hand or a paper. If you do, you can see that the number printed on the serial monitor becomes smaller and the brightness of the LED becomes darker. Well, in this tutorial, I have given another practical exercise that a photoresistor measures the brightness of the light, and also I have conducted a fun experiment to adjust the brightness of the LED according to the brightness of the environment. Thank you. Hi everyone. In this tutorial, we'll develop an Arduino program to measure the distance by using a sensor. The sensor to be used for this tutorial is an infrared proximity sensor. This sensor allows you to measure distances to obstacles using infrared rays. The distance from the obstacle can be detected from around 10 centimeters to 80 centimeters. When measuring an obstacle at a distance of 10 centimeters, it has an analog output voltage of about 3.1 volts and an output voltage of about 0.4 volts is needed when measuring an obstacle at a distance of 80 centimeters. Therefore, the distance from 10 centimeters to 80 centimeters have analog output voltages between 3.1 volt and 0.4 volt. In actual measurement, it does not indicate how many volts the output voltage is going to the output, but it'll come after converted to a value between 0 and 1023. So if you have used a formula that converts the analog output voltage between 0 and 1023 into a distance, you can measure the distance from the obstacle to the center accurately. If you open the serial monitor, you can monitor the distance from the obstacle in real time. Now let's configure the circuit connecting the infrared proximity sensor to the Arduino board is very simple. 3 cables are needed to connect this sensor. As shown on the slide, you should connect the sensor to the ground, a power supply volt of 5 volts, and to the analog port A0 for measuring the distance. Now let's make the sketch for this. First, we'll assign the power supply voltage 5 volt to the variable VCC. We'll use the variable distance to store the result of the output. And we have set the speed of serial communication to 9600 bits per second because serial communication with sensor is required. The loop function contains a formula that converts the analog output voltage measured by the sensor to a distance. The measured value is loaded using the analog read command. This value is between 0 and 1023 and is expressed in 10 bits. Therefore, we should separate this value by 2 to the power of 10 or 1024 cases. Then, when the formula for converting the voltage to the distance is passed, the distance between the sensor and obstacle is obtained. The relationship between the sensor's output voltage and the inverse of the measured distance is approximately linear over the sensor's usable range. The infrared proximity sensor contains a plot analog output voltage as a function of the inverse of the distance to a reflective object. You can use this plot on the right to convert the sensor output voltage to an approximate distance by constructing a best fit line that relates the inverse of the output voltage to distance, as shown in the right graph. With this, the core of the loop function is done, and we're going to work on outputting to the serial monitor. And at the end, by giving a 0.3 second delay, we will be able to see the measurement results visually. Now, compiling and uploading the sketch will make the infrared proximity sensor measure the distance to the obstacle. In this tutorial, we looked at practical exercise which used an infrared proximity sensor to measure the distance to the obstacle. Hello everyone. In this lecture, I will introduce Raspberry Pi, which is another popular device development platform frequently used to develop IoT applications. Here is a table of contents for this lecture. First, I'm going to introduce what Raspberry Pi is. I will then explain the hardware components of the Raspberry Pi. Then I'm going to introduce the software used for Raspberry Pi, as well as some interesting projects using Raspberry Pi. So, what is Raspberry Pi? The Raspberry Pi is a series of small single board computers developed by UK-based Raspberry Pi Foundation to promote the teaching of basic computer science in schools and in developing countries. The Raspberry Pi is a credit card-sized computer that plugs into your TV or a computer monitor and a keyboard. It is a capable little computer which can be used in electronics projects and for many of the things that your desktop PC does, like spreadsheets, word processing, browsing the internet, and playing games. The Raspberry Pi Foundation is a charity organization founded in 2009 in United Kingdom to promote the study of basic computer programming in schools, kindergarten, elementary, middle, and high schools, and in developing countries. It is responsible for developing the Raspberry Pi. The foundation is supported by the University of Computer Laboratory at Cambridge University and a semiconductor company called Broadcom. Its aim is to promote the study of computer science and related topics, especially at school level, and to put the fun back into learning computing. There is no separate foundation's official homepage, but you can find a simple introduction on the Raspberry Pi homepage. Originally, the Raspberry Pi was designed for education. They thought that the Raspberry Pi will be helpful for young students who are at the pre-university level to improve programming skills and hardware understanding if they use a low-cost device such as Raspberry Pi. So the Raspberry Pi Foundation provided low-cost computers that people use to learn, solve problems, and have fun. But thanks to its small size and accessible price, it was quickly adopted by thinkers, makers, and electronics enthusiasts for projects that require more than a basic microcontroller, such as Arduino. The Raspberry Pi is slower than a modern laptop or a desktop, but it is still a complete Linux computer and can provide all the expected abilities from a computer. Many people think that Raspberry Pi is an eating pie made of raspberries. So people who do not know these areas have questions about why they call computers pie. However, if you look closely at the name, it is not pie. It is not Raspberry Pi, but Raspberry Pi. Raspberry means that the fruit we think is right, but not a pie to eat. As you can see, pi is related to Python. So, where does the name Raspberry Pi come from? Raspberry is a reference to a fruit naming tradition in the old days of microcomputers. A lot of computers names were named after fruit. Examples of these are Apple from US, BlackBerry from Canada, Tangerine Computer Systems from UK, Apricot Computers also from UK, and the old British company Acorn, which is a family of fruits. Pi is because originally they were going to produce a computer that could only run Python language. So the pi in there is for Python. For most people, Python is the easiest language to learn than C or C++. Several generations of Raspberry Pis have been developed. Let's compare the Raspberry Pi models released so far. The Raspberry Pi Model B was launched in February 2012 at a price of $35. This model has two USB 2.0 ports. There is a slot to be inserted SD card for the external storage device. Model A was released at a price of $25 in February 2013. Although this model was released a year later than Model B, it was cheaper. This model has a single USB port and an SD card slot. In July 2014, Model B Plus was released at a price of $35. This model has 4 USB ports. Compared to the Model B, released 2 years earlier, the number of US ports has increased, and it also provides a micro SD card slot. In November 2014, Model A Plus was launched at a price of $20. This model has 1 port of USB and a micro SD card slot. Compared to Model A released a year ago, the price has become cheaper. Upgraded models have been released since the first generation models. As the second generation of Raspberry Pi, Model B was launched at a price of $35 in February 2015. This model had 4 USB ports and a micro SD card slot for additional external storage. It is providing more and improved features, but at the same price as the original Model B, released 3 years earlier. It also provides better performance than the original Model B Plus, released an year earlier at the same price. In November 2015, Raspberry Pi Zero was released at a price of $5. It is good to use it for IoT applications because it is very small in size and very cheap. In February 2016, the Model B of the 3rd generation was launched at a price of $35. Many parts of this model have improved performance compared to the 2nd generation Model B, released a year ago. Additionally, both Wi-Fi and Bluetooth are supported in this model. Detailed info on all models and accessories can be found at the Raspberry Pi products page. Let's look at the Raspberry Pi hardware components. The hardware configuration of a Raspberry Pi is shown in the image on the slide. First of all, looking at the center of the board, you can see a computer chip. It is a SoC, or system on chip. This chip has various functions, such as ARM core processor, graphics processing unit, or GPU, and various kinds of interfaces. And there are a couple of USB ports. You can connect a mouse, keyboard, and etc. to the USB port. And if you want to connect more USB cables, you can use a USB hub next to the USB port is an Ethernet port that you can connect a LAN cable to the internet. You'll also need a monitor to view the screen in order to make sure what is going on the Raspberry Pi. The monitor can be connected through the HDMI port. The power of the Raspberry Pi board can be supplied by using USB micro B type. And there is a slot for inserting a micro SD card, which acts as a hard disk in the computer. Finally, there is GPIO, or general purpose IO pins. Here you can connect electronic components such as LEDs, switches, and sensors. To use a Raspberry Pi as a complete computer, you need several peripherals. You need a monitor, keyboard, and a mouse, as well as an HDMI cable, a power cable, and an SD card. So if you connect all the peripherals to the Raspberry Pi, it will become one complete computer, as shown in the image on the right. Let's compare the components by respectively Raspberry Pi model. The models on the left are the more recently released models. Compared to the models on the right, released in the past, the recent Raspberry Pi 3 Model B has more enhanced CPU, GPU, and RAM. More importantly, it has been supporting wireless communication functions that were not supported by previous models. The price did not go up in spite of the improved performance. It's equally priced at $35. Now, let's look at what kind of software is available for the Raspberry Pi. Basically, Raspberry Pi is a blank computer without operating system. So you have to install the operating system, or OS, on the board. The most commonly used OS is Raspbian, which is based on the Linux distribution called Debian. Raspbian includes a variety of applications such as web browser, Python, and Scratch. If you wish, you can install other OS on Raspberry Pi. For example, you can install Ubuntu Mate, a Linux distribution for Raspberry Pi. Snappy Ubuntu Core is the lightweight core of Ubuntu. I think it is good to use it for IoT. The Windows 10 IoT Core is a distribution edition from Microsoft that supports the Windows 10 version for Raspberry Pi. In addition, you can install various operating systems such as OSMC, RISC OS, Fedora, CentOS, and Kali Linux as Raspberry Pi OS. As the basic OS of Raspberry Pi, Raspbian has some applications to help you use Raspberry Pi. If you use Epiphany, a standard web browser in Raspbian, you can use the internet in Raspberry Pi. There's a file manager similar to File Explorer in Windows. There is a terminal application, LX Terminal, that can execute various instructions. Mathematica is a professional mathematical application that handles calculations, graphs, and so on. Sonic Pi is an educational application that lets you learn programming as you create music. In addition, you can enjoy the most famous 3D graphics game, Minecraft, in Raspbian. Scratch is a visual programming tool developed by the MIT Media Lab. It allows the user to create animations and games with a drag and drop interface. It is a great way to get started programming on Raspberry Pi with young people. It allows you to create your own computer games, interactive storage, and animations using some programming techniques without actually having to write any code. To find more about Scratch, visit its website at scratch.mit.edu. Python is one of the most popular languages in the world and has been around for more than 2 decades. It is heavily used in academic environments and is a widely supported platform in modern applications, especially utilities and desktop and web applications. Python syntax is very clean, with an emphasis on readability and uses standard English keywords. Therefore, Python is recommended as a language that is easy for newcomers to program. Now, I'd like to introduce several interesting projects using Raspberry Pi. Well, at Southampton University in UK, they developed a high-performance supercomputer using dozens of Raspberry Pis and Legos. For more details, please visit the Southampton website and watch their YouTube videos. There was also an interesting project to make a quadcopter using Raspberry Pi. It was developed by the Warwick University in UK. You can visit its website for more details. There was a project that sent Raspberry Pi to the sky with a hot air balloon. Raspberry Pi came back after going up to about 40 kilometers and taking pictures from the sky. There are many websites providing various info about Raspberry Pi. Raspberry.org is the official website of the Raspberry Pi. It provides information on all the Raspberry Pi products available, downloading available operating systems, various forums, and many interesting projects developed using the Raspberry Pi. You can find more info on Scratch and Python programming languages as well. Hello everyone. In this lecture, I will introduce how to set up and use Raspberry Pi. Raspberry Pi 3 is a 3rd generation Raspberry Pi. It replaced the Raspberry Pi 2 Model B in February 2016. We will use the latest Raspberry Pi 3 model for this lecture. A monitor or TV with HDMI cable can be used as a display with the Raspberry Pi. We will also need HDMI to HDMI cable, a USB port, USB keyboard, and USB mouse will also be needed. And a micro USB power supply is needed. A micro SD card instead of SD card is used to store operating system and data on your Raspberry Pi. Raspberry Pi is a fully blown computer without an operating system. When you get a new Raspberry Pi, you have to download and install an operating system by yourself. Although there are many operating systems you can install and use, the most commonly used operating system is Raspbian. Raspbian is a standard distribution optimized for Raspberry Pi. There are 3 ways to install Raspbian. First, using Noobs. Second, use Noobs Lite. And third, download only Raspbian image file. Noobs is software that installs the operating system in Raspberry Pi. If you use Noobs, Noobs makes it easy for you to install an operating system. You can download Raspbian and Noobs by visiting the given URL. First, in order to install an operating system in the Raspberry Pi, you need to download the Raspbian OS onto the Raspberry Pi. This Raspbian OS must be stored on a micro SD card. This can be achieved by downloading the Raspbian OS onto your PC and then copy it to a micro SD card using a USB-based SD card reader. Then you can insert the micro SD card into the Raspberry Pi board to boot the operating system. This slide illustrates 2 ways to install Raspbian on the Raspberry Pi. One is to use Noobs, and the other is using the Raspbian image. When using Noobs, unpack the Noobs file and then copy to micro SD card. After inserting micro SD card into Raspberry Pi, you can install Raspbian using the Noobs program. If you download only the Raspbian image file, you need to unzip the image file and then copy to the micro SD card. If you insert the micro SD card into Raspberry Pi, you can run the Raspberry Pi immediately. Although it is very convenient to install the OS this way, you may need to configure the system yourself. Go to the following website and download Noobs or Raspbian image file. In this lecture, I will explain how to install the OS by downloading the Raspbian image file. First, unpack the downloaded image file. You should use a tool like Win32 Disk Imager to write a Raspbian image into a micro SD card. Please visit this website to download and use Win32 Disk Imager. Please install it after downloading Win32 Disk Imager. Now, run Win32 Disk Imager and write the previously downloaded Raspbian image file onto the micro SD card. After the Raspbian OS is stored on an micro SD card, you can plug in the Raspberry Pi as follows. First, begin by placing your micro SD card into the micro SD card slot on the Raspberry Pi. It will only fit one way. 2. Plug your USB-based keyboard and mouse into the US ports on the Raspberry Pi. 3. Make sure that your monitor or TV is turned on and that you have selected the correct input. For example, HDMI 1, DVI, etc. 4. Connect your HDMI cable from your Raspberry Pi to your monitor or TV. Step 5. If you intend to connect your Raspberry Pi to the internet, plug an Ethernet cable into the Ethernet port, or connect a Wi-Fi dongle to one of the USB ports. Step 6. When you have plugged in all the cables and micro SD card correctly, connect the micro SD power supply. This action will turn on and boot your Raspberry Pi. The Raspberry Pi will now boot as follows. As soon as the power is applied, the board will be booting. The boot process will take a few seconds. Raspbian operating system has started and is now fully running when you see this picture. You will probably want to connect your Raspberry Pi to your local network or the internet. You can use any of the following connecting options to do this: Ethernet or Wi-Fi. If you have a Raspberry Pi 3, then there is a built-in Wi-Fi. If you're using an earlier version of the Raspberry Pi, then you'll need to use an USB Wi-Fi dongle. Some Wi-Fi dongles, when used with the Raspberry Pi, are simple plug-and-play devices. Others require specific drivers and may not be compatible with the Raspberry Pi. Please make sure you read the device manufacturer's documentation before making a purchase. The Raspberry Pi has an Ethernet port right beside the USB ports. If your Raspberry Pi is situated close to a router, access point, or a switch, you can connect it to a network using an Ethernet cable. Once you have plugged in the Ethernet cable into the Raspberry Pi and the other end into an access point, your Raspberry Pi will now connect to the network. If the Raspbian is booted normally, the language of the system will be set to English. If you wish to add Korean Hangul fonts, you must do the following. In order to input commands to Raspbian, you need to start LX Terminal application, which is a Linux terminal Windows software. First, the Raspberry Pi board must be connected to the internet, and then typing upgrade commands you can download the latest package. If you open the download package, you will know that Hangul is included in the downloaded package. Using the install command, you can install Hangul fonts to Raspbian. After the Korean language installation is completed, it should be reflected in the system. Please enter the Raspberry Pi configuration as shown on the slide. On the Localization tab, click Set Locale, then select Korean as shown and click the OK button. You should also change the runtime setting to Korean time. Please select Asia, Seoul for the area location in the time zone. Finally, go into Set Keyboard and set it to Korean. Let's reboot it now, and after rebooting the Raspberry Pi, you can see that all English commands and menus are in Raspbian have been changed to Korean. If you want to input Hangul, please select Hangul instead of US in the language option. And if you check Hangul status, you can input Hangul from now. When you wish to change back to English or return to Hangul, you can easily switch back and forth by pressing the Shift and spacebar together. Since Raspberry Pi is an independent computer, it usually requires a separate monitor, keyboard, and mouse. But what if you do not have an extra monitor, keyboard, or mouse? Can you still use the Raspberry Pi? The answer is yes. So, being able to access the Raspberry Pi without its own monitor, keyboard, mouse is called headless setup. The software that makes it possible is called VNC, or Virtual Network Computing. Let me briefly explain the principle of VNC. If you're running a VNC server on Raspberry Pi, you can remotely access it using the VNC client on your PC. Let's install VNC. First, please download the appropriate version for your PC's operating system from the VNC homepage. Since you do not need a VNC server on your PC, select VNC Viewer, not the server, and complete the installation. You should now install VNC Server on your Raspberry Pi. First, you should check the IP address of the Raspberry Pi, which is needed when installing the VNC server. This can be achieved by executing a command called ifconfig. There are two ways to access Raspberry Pi via VNC. The first is to open a new connection whenever you access it. And the other is to keep going to only one connection and share this connection. Of course, the first method is the default method and is faster. The second is a little slower because multiple users can share at the same time. Let me explain both methods here. The first method is as follows. Install the VNC server. After installation, set the port number to random and run the VNC server. On your PC, run the VNC viewer and enter the port number along with the IP address of the Raspberry Pi. For example, 141.23.83.21.1 is an IP address of your PC, and 1 will be the port number. For security reasons, it will require to input a password for Raspberry Pi. If you enter the password correctly, you can remotely access Raspberry Pi from your PC using VNC as shown on the slide. The second way to keep and share only one connection. Install a different version of VNC than before and run the VNC server. You can see that the commands are slightly different from the first method. On your PC, please enter only the IP address of your Raspberry Pi in the VNC viewer. This is because Raspberry Pi keeps only one connection. Likewise, a password can be required for security. If you enter the password correctly, you can see that you have remotely connected to Raspberry Pi on your PC as shown. Well, in this lecture, I explained the hardware requirements for getting started. I explained the major parts of Raspberry Pi 3 Model B and 2 methods for installing Raspbian operating system on the Raspberry Pi. I then explained the concept of headless setup and how to achieve it using VNC server. In the following lecture, I will explain how to program Raspberry Pi. Hi everyone. In this lecture, I'll go through the first tutorial to make the LED on the Raspberry Pi blink. It is very simple, and it is the easiest way to understand how GPIO or general purpose input-output works. Here are the required hardware components for turning on the LED on the Raspberry Pi. We need a Raspberry Pi, of course, a breadboard, red LED, resistor, and jumper cables. In order to light the LED, the current above a certain value must flow. Too little current will not turn on the LED. Conversely, if too much current flows, the LED will burn out. Therefore, a resistor is required to allow a proper amount of current to flow. The smaller the resistance, the more current flows, and the brightness of the LED becomes brighter. The LED has polarity. Among the two legs of the LED, the long side is called anode, plus. The short side is called cathode, minus. The resistor has no polarity, however. The breadboard consists of power rails and terminal strips. Each power rail is horizontally connected internally. On the contrary, each terminal strip is vertically connected internally. The description on the breadboard was already given during the Arduino tutorial, and basically the functionality is the same here. The circuit configuration for turning on the LED is quite simple. First, connect the cathode pin of the LED with the ground pin of the Raspberry Pi board. At this time, you have to connect the two pins using jumper cables. And then connect the anode pin of the LED with the ballast resistor. The resistor has no polarity, and thus you do not have to worry about the connecting direction of the resistor. Finally, connect the opposite pin of the resistor with pin GPIO 17 on the Raspberry Pi board. Now that you have configured the circuit, you should write a Python program to operate the circuit. You can write a simple code that blinks the LED as shown on the right. You need to import Python GPIO module to use it. And you have to define a function called blink. You need to set GPIO high to turn on the LED. Then you have to insert the time sleep command to have a stop time of the LED for 1 second to see if the LED is on and off normally. The blink function now cycles through turning the LED on and off for 1 second. To start the operation, you need to set pin mode to BCM and pin 17 to output. The GPIO set mode function is a function that sets which reference method to use when assigning pin numbers. GPIO.BCM means to refer to GPIO number of Broadcom chip. Unlike programming for Arduino, there's not a single integrated software for writing, editing, compiling, unloading in Raspberry Pi. You have a choice of text editors. Some are easy to use but have limited functionality. Others require training to use and take a long time to master, but offer incredible functionality. For desktop graphical editors, there are LeafPad, Idle, and GVIM. For command line editors, there are Nano, VI, VIM, and Emacs. Python is an interpretive language, not a compiled language. Thus, Python interpreter is provided in Raspbian, and you can execute a Python program by simply typing Python and program name on a command line interface. Now, when you execute the program, you can see that the LED installed on the breadboard flashes at 1 second intervals. In this tutorial, I have explained how to set up the circuit to blink the LED connected to the Raspberry Pi. Let me wrap up this tutorial here. We'll see you shortly. Thank you. Hello everyone. In this lecture, I'll go into the practice of measuring the brightness of light. Analog and digital signals are used to transmit information, usually through electrical signals. In both of these technologies, the information, such as audio or video, is transformed into electrical signals. The difference between analog and digital technologies is that in analog technology, information is translated into electrical pulses of continuous amplitude. In digital technology, translation of information is into binary format, 0s or 1s, where each bit is representative of two discrete amplitudes. However, when we try to use a sensor, the sensor plays a role to collect analog data around us. And then we can read them because it converts the analog data into digital data. The sensor we will cover in this lecture is a sensor called photoresistor. Another term for it is called light-dependent resistor, or LDR. This is a sensor whose resistance value increases or decreases with the amount of light. So the circuit to be constructed in this tutorial has the following characteristics. LED will be turned off or on according to the brightness of the surrounding environment. If the surroundings are dark, the LED will be turned on. And if the surroundings are bright, the LED will be turned off. In order to measure the brightness of light in the environment and to turn on and off the LED, we need the following components: Raspberry Pi, breadboard, red LED, 430 ohms resistor, one photoresistor, 3-pin, and jumper cables. Circuit configuration is very simple. You need to connect the cathode pin of the LED with the ground pin on the Raspberry Pi board. And you need to connect the two pins using jumper wires. The anode pin of the LED is connected with a ballast resistor. The resistor does not have polarity, so you don't have to worry about the direction of the connection. Now, connect the opposite pin of the resistor with the pin 18 on the Raspberry Pi board. We are going to make a LED that responds to brightness. So we need to connect the photoresistor to measure the brightness. Connect the VCC of the photoresistor with the 3.3 volt pin of the Raspberry Pi board. You have to connect out with pin 17 of GPIO. Finally, connect ground with the ground pin. Now that you have configured the circuit, you should write a program to operate the circuit. You need to use Python GPIO module, so import it. Since we need to refer to the number GPIO of Broadcom chip, you have to set GPIO.BCM mode. You need to set pin GPIO 17 to in, because you need to measure the amount of light by connecting a photoresistor to pin number 17. You also need to set pin 18 to out, because the LED must be on according to the surrounding brightness. Then check the value of GPIO 17 every second. If the value of GPIO 17 is 0, it means that the surrounding area is bright. At this time, LED is not turned on. You can now set low for GPIO 18. In GPIO 17, or if GPIO 17 is 1, then it means that the surroundings are dark. At this time, you should turn on the LED. You need to set high to GPIO 18. Then sleep for 1 second and then do the same checking again. Let's try to run it. If the surrounding area is bright, the LED will not turn on and will display bright on the screen. When you cover the photoresistor by hand or darken it, dark will be displayed on the screen and the LED will lighten up. Well, let me wrap up this tutorial here and I'll see you shortly. Bye for now. Hi everyone. In this lecture, I will explain how to measure the distance by using an ultrasonic distance sensor. An ultrasonic sensor is a device that can measure the distance to an object by using sound waves. It measures distance by sending out a sound wave at a specific frequency and listening for that sound wave to bounce back. By recording the elapsed time between the sound wave being generated and the sound wave bouncing back, it is possible to calculate the distance between the sonar sensor and the object. Since it is known that the sound travels through the air at about 344 meters per second, you can take the time for the sound wave to return and multiply it by 344 meters to find the total round trip distance of the sound wave. Round trip means that the sound wave traveled 2 times the distance to the object before it was detected by the sensor. It includes the trip from the sensor to the object and then the trip from the object to the ultrasonic sensor after the sound wave bounced off the object. To find the distance to the object, you simply divide the round trip distance in half. Well, there are some preparations before the experiment can take place. We need the following components: 1 Raspberry Pi, 1 breadboard, 2 430 ohm resistors, 1 ultrasonic sensor, and jumper cables. Circuit configuration for this is also very simple. You need to connect the VCC pin of the sensor with the 5-volt pin of the Raspberry Pi board. The trig of the sensor should be connected with the pin GPIO 18. Trig is an abbreviation of a trigger and sends ultrasound to an object via the pin GPIO 18. The sensor's echo should be connected with 2 resistors. The resistor has no polarity, so you don't have to worry about the direction of the connection. Finally, the ground pin of the sensor should be now connected with the ground pin of the Raspberry Pi board. Now that you have configured the circuit, you should now create a program to operate the circuit. The complete code is given on the slide. First, you need to set the GPIO pin 18 as the output mode to transmit the ultrasonic wave. You then should set pin GPIO 24 as input mode to receive the returning ultrasonic wave. To transmit ultrasound, you have to set pin GPIO 18 to true, and then in a moment change it to false. Now that we've sent our pulse signal, we need to listen to our input pin, which is connected to echo. The sensor sets echo to high for the amount of time it takes for the pulse to go and come back. So our code, therefore, needs to measure the amount of time that the echo pin stays high. We use the while loop to ensure that each signal timestamp is recorded in the correct order. The time function will record the latest timestamp for the given condition. So it measures the time it takes echo to go from high to low. This is the time for the ultrasonic signal to travel to the destination and back to the starting point. Distance is the time times speed. Therefore, the distance to be measured can be obtained by multiplying the sound speed of 34,300 by the time and dividing it by 2, because a single distance should be measured instead of a round trip. Now you can execute the program to measure the distance from an object. As you move objects closer to or farther from the sensor, you can see whether the sensor measures the distance well. Well, that's it for this edition of tutorial for the Raspberry Pi. I hope this will get you started using the Raspberry Pi to develop interesting applications. Have fun.
Hello everyone, I'm Professor James Won-gi-hong from the Department of Computer Science and Engineering at Post-Tech. Today I will introduce Arctic, which is fairly new, but a powerful IoT device development platform in the world. Here's a table of contents for this lecture. First, I'm going to introduce what Arctic is. I will then explain some series of Arctic modules. Then I'm going to introduce the software used for Arctic, Arctic Cloud, and interesting projects using Arctic. Before introducing Samsung Arctic to you, let's watch a couple of videos that describe Samsung Arctic and IoT. If you have not watched the videos, please do so before you going further. It will give you a good understanding of Arctic at the very high level. So, what is Arctic? Well, Arctic is the IoT development platform developed by Samsung Electronics. Arctic is the integrated IoT platform that provides the fastest path to deliver secure, interoperable, and intelligent IoT products and services. Samsung Arctic unifies hardware, software, cloud, security, and partner ecosystem in a single integrated offering. The Samsung Arctic Smart IoT platform brings hardware modules and cloud services together with built-in security and then ecosystem of tools and partners to speed up the development and time to market. Arctic module is hardware to drive a wide range of devices, from tiny things to IoT hubs and gateways. Arctic modules are tightly integrated with the Samsung Arctic IoT platform. Arctic Cloud is an open, unified set of key IoT features like user, data, and device management, a sophisticated orchestration engine, tight security, and more. Most important, Arctic Cloud has built-in services to allow developers to connect all devices and cloud services to each other. Some IoT applications need to secure sensitive data locally on the module. Arctic provides a secure OS as well as secure software to store data safely on the devices. Arctic also provides a software interface to enable many common security operations. They are building a growing family of partners to help users with custom engineering, system integration, and training. Samsung Arctic integrates all of the components users need to bring users' business into the world of IoT. They call it end-to-end IoT. The following figure illustrates the structure of Samsung Arctic end-to-end IoT platform. Arctic users can get various functions with Arctic ecosystem environment. First, you can connect Arctic modules to the cloud. With the Arctic modules optimized for the Arctic Cloud, users can develop IoT services and generated data can be managed in the Arctic Cloud. Compatibility with other products is also an important feature. You can manage the IoT devices on the cloud, which were made by third party, more systematically and securely by linking them with the IoT Arctic Cloud. Finally, you can improve your IoT business based on these capabilities. Mobile applications allow users to monitor data and receive analysis services. Arctic Cloud is an open data exchange platform for the Internet of Things, designed to accelerate device interoperability and enable new data insights. Arctic Cloud can receive data from a variety of devices. Clients can use many different protocols to send and receive data, including REST, WebSockets, MQTT, and CoAP. You can get data from devices that are already communicating with third-party clouds into the Arctic Cloud. Arctic Cloud enables communication with various IoT products. So, if multiple IoT devices are being managed in different IoT clouds, Arctic Cloud can manage them all together. Now, let's look at various Arctic modules. They've divided modules into families based on size, power, and capabilities. Let's discover Arctic module families. Arctic 0, 5, 7, and 10. Samsung Arctic 0 family of IoT modules is designed to be tiny, specifically for the things in IoT. They provide Bluetooth, Zigbee, or Wi-Fi built-in capability. Arctic 053, bringing Wi-Fi to things that need compactness and connectivity, but without sacrificing security. Arctic 053 model has a built-in security module that keeps its factory-installed certificates and keys safe, runs Tizen real-time OS, and supports open-source development tools. Arctic 020 model includes a Bluetooth, targeted for Bluetooth Low Energy or BLE applications, where reliable RF, low power consumption, and initial industrial grade application development are key requirements. Arctic 030 is a fully integrated, pre-certified module for wireless mesh networking solutions using Zigbee or Thread protocols. It combines an energy-efficient multi-protocol wireless SoC with proven RF antenna design and wireless software stacks, and an industrial-grade development environment. Arctic 5 family of IoT modules is designed for low cost, balancing power, and performance for gateways, display-based applications. Formerly known as Arctic 5, Arctic 520 offers target devices a good combination of computing power and storage capability for its size. Multiple wireless options include Wi-Fi, Bluetooth 4.1, Bluetooth Smart, Zigbee, and Thread. Arctic 530 takes Arctic 520's combination of power and multimedia and adds power while reducing cost. Arctic 530 features a quad core processor for local data processing and a multimedia engine to handle audio and video processing. The modules also support most of the commonly used local area wireless standards such as 82.11, Bluetooth, Zigbee, and Thread. The Samsung Arctic 7 family of IoT modules shows great performance with local processing and analytics, and for multimedia applications. Arctic 710 gives you 8 cores to serve effectively as a gateway for a large building or factory, and also run local analytics to improve latency and responsiveness. It also provides multiple connectivity solutions to communicate with your things, and has a high-end multimedia processor to handle video and audio processing. With a combination of Wi-Fi, Bluetooth, Zigbee, Thread, the Arctic 710 module is a good choice for home automation and home hub devices, while also supporting a rich UI UX capability with the camera and display support options. Samsung Arctic 1020 module makes it ideal for applications with high local computation requirements, like model-based robotic control, virtual reality, and image processing. It has built-in DRAM and flash memory, camera and display interfaces, plus a full complement of digital I/O and analog inputs. Note that the new development of high-performance IoT products should be based on Samsung Arctic 710, as the Arctic 1020 is no longer in production. Samsung says that limited stacks of Arctic 1020 modules and developer kits are still available for experimentation and small-scale products. Now, let's look at what kind of software is available for the Arctic modules. By default, the Samsung Arctic module supports the Tizen operating system. Tizen is an operating system created by Samsung. It is mainly equipped with electronic devices and home appliances manufactured by Samsung. Then you may ask whether other operating systems are supported by Arctic. The simple answer is yes, because it is based on a Unix-driven hardware architecture, and therefore any Unix variant is feasible in principle. So other operating systems such as Fedora, Snappy Ubuntu, and Resin OS can be installed on the Arctic module. The Arctic IDE is a fully integrated development environment for Arctic 053, 520, 530, and 710. It includes SDK packages, toolchains, and debug tools to enable Linux and Tizen real-time application development on Arctic modules. Also, users can use various IDEs for development. Arduino IDE is an easy-to-use sketch-based development environment for Arctic 5, 7, and 10. Node RED is a visual wiring tool for drag and drop development based on Node.js. For expert Eclipse users, they provide the environment you will need to develop for Arctic 5, 7, and 10. Resident.io is a cloud-based build and deployment environment. Now let's briefly have a look at what Arctic Cloud provides. Arctic Cloud is an open and interoperable data exchange platform for the Internet of Things. It enables Arctic-based devices to communicate with other hardware devices, apps, as well as cloud services. It can collect any data, discrete, continuous, real-time, or historic. Arctic Cloud connectors allow you to easily integrate an existing cloud with Arctic Cloud. It provides data analytics as well as visualization capabilities. We will have an in-depth study on Arctic Cloud in a separate lecture. Now, I would like to introduce several interesting projects using Arctic. Since Arctic is a newcomer compared to Arduino and Raspberry Pi, there are not as many IoT applications that use Arctic yet. I'm sure we'll see more interesting IoT applications that use Arctic modules in the near future. This first application is a water tank application using IoT technology. If there's a shortage of water, the alarm will automatically come on and the water will fill up. The Arctic board is used here. In the second application example, a woman demonstrates 3 smart trash cans, each powered by a Samsung Arctic board and connected via MQTT. Using a combination of Zendesk, Nexmo, and Google Calendar APIs, she creates tickets to notify facility managers when the trash cans have reached capacity and must be emptied. The third example, a woman used Samsung Arctic and Arctic Cloud to monitor temperature and garden moisture levels and control them with connected fans and water pumps. Now, please take a few minutes watching those videos and see how they've used Arctic modules for their applications. Here are some websites providing various info about Arctic. The first reference, Arctic.io, is the official website of Arctic. It provides information on all the Arctic products available, tutorials, as well as forums. In this lecture, I gave an introduction to Samsung Arctic family of modules. In the next lecture, I will explain how to get started with a Samsung Arctic development kit. See you soon. Hello everyone. I'm Professor James Won-gi-hong from the Department of Computer Science and Engineering at Post-Tech. Today, I will introduce how to get started with Arctic development kit. Most of the materials for this lecture are from the Arctic's official website and developers' website. Here is a table of contents for this lecture. First, I'm going to introduce how to get started. I will then explain what hardware components are included in the Arctic Development Kit box. I will then explain other hardware needed, including power adapter and USB cable. Sensors, accessories, and 2 antennas for Zigbee, Wi-Fi, Bluetooth protocols will be explained. I will also explain how to power up and activate the development board and connect to your computer. I will also explain how to install and use the Arctic IDE, Integrated Development Environment software. Here are the steps for getting started with Arctic 710 development board. First, go to the Arctic official website, www.arctic.io. Then click Start Developing link. And then click Arctic 710 Get Started link. Please watch the Arctic 710 Training 1 video, Getting Started. And then click in the box board reference on the left bar menu under Arctic 710 Getting Started. We will be using Arctic 710 Development Kit for this course. When you open an Arctic 710 Development Kit box, you will find the following: Arctic 710 module mounted on a development board, separate plug-on interface breakout board, and 2 wireless communication antennas. Well, what else do you need? You will need the following in order to use the Arctic 710 Development Kit. Correct 5-volt DC 24-watt adapter. Please note that your power supply is 5-volt, not 12-volt. The plug ends are identical, so look at the adapter ratings plate before continuing. USB A to micro B cable for connection from your host PC to the debug USB port micro USB receptacle of your Arctic board, or choose a different cable if your host PC does not use a USB A plug-in. Third, connection to local Wi-Fi. You can get started without this if needed. USB cables with correct plugs to match between your host platform and certain board-specific USB ports you may eventually want to use. You won't need these right away. 5. HDMI micro to standard cable. If you have an Arctic 530, 710, or 1020 and plan to connect HDMI display. For the Arctic board details, you should look at the datasheet section for the documentation on the boards and modules. For this lecture, we will skip that, but please have a look when you have a chance. Arctic modules are static sensitive devices, so please make sure you ground yourself and observe proper SCD safeguards when handling modules and development boards. The left image is exposed portion of an interposer board, and the right image is its bottom side. The interposer board holds the Arctic module itself and provides video and wireless connectivity. The left image is exposed portion of a platform board, and the right image is the other side. The platform board attaches to the underside of the interposer board to provide additional interface circuitry, such as a connector to interface board, audio jack, micro SD card slot, and so on. The interface board, shown attached to the interposer and platform board assembly, breaks out the external interface signals to larger connectors. There are two antennas included in the development kit, one for Zigbee and one for Wi-Fi, Bluetooth. Both are identical and interchangeable. The following add-ons are offered for purchase separately from the development kit: MIPI camera, sensor board, including sensors such as humidity, temperature, accelerometer, gyroscope sensor, etc. MIPI touchscreen LCD 5-inch display. LVDS touchscreen OLED 7-inch display. Details on these accessories can be found on the Arctic developers website. Now, let's prepare for powering up the development board. We need to check jumpers first. The platform board on the underside of the board with the Arctic 7 module has a set of jumpers, JP1 to JP4. These jumpers select whether power comes from the 5-volt DC adapter or the battery. Jumpers 2 and 3 is normal. The 5-volt DC adapter powers the board and charges the battery if present. Battery will not power board if adapter is unplugged. Jumpers 1 and 2. Battery. The battery powers the board but must not be charged. If battery is present, disconnect the adapter. With battery disconnected, adapter may be connected to power the board. Whenever jumper 1 to jumper 4 are in the 1-2 position, connect either battery or the 5-volt DC adapter. Battery damage can occur if both are connected. Now, connect the board to your computer with USB cable. There are 2 micro USB connectors on the board assembly. Use the debug USB on the bottom board as shown. Now, connect the antennas. One long antenna screws onto the Wi-Fi on the board directly over the USB cable you just connected, and the other screws onto the Zigbee radio connector. Since the antennas are interchangeable, you do not have to worry about which antenna to connect to where. Before connecting the power to the board, make sure the power switch on the development board is set to off position. Plug the AC side of the 5-volt power supply into your power outlet and the other end into the development board. Slide the power switch on the development board rightward to the on position. Note that this is like putting the battery in your cell phone. It doesn't turn the board on, just gets it ready to turn on. Observe that the LEDs on the underside lights up. Do not press the software to power button at this time. Wait until the instruction in the next section to do so. You are now ready to move on to the next step, which is activating the board. Here is how you activate the board initially. After you first apply power, you'll need to activate the board with a 1-second reset button using the power on, using the power push button switch. Once the power circuit has been activated, pushing it again has no effect. Use the reboot command to restart. Doing so ensures that files are properly closed before restart commences. For an ordinary power down sequence, use the shutdown now command. For a forced restart, the reset button located next to the 710 power button forces the module to restart. The Arctic Integrated Development Environment is provided for Windows, Linux, and Mac. The Arctic IDE is used for easy application development on Arctic modules. Arctic IDE installer includes all the software SDK packages, tools, and drivers required to build and debug applications. Although we will explain how to install, configure, use the IDE for Windows, but all the info needed for Linux and Mac are also available on the Arctic developer website. The system requirements for installing the Arctic IDE are as follows. Microsoft Windows 7, 8, or 10, 3 gigabytes of RAM, 2.5 gigabytes of disk space, 1280 by 800 screen resolution. We recommend that Windows users install the Arctic IDE. As part of its complete development environment, it integrates a convenient terminal emulator program that you can start using right away to talk to your Arctic board. The latest Arctic IDE can be downloaded from the following website. Install the Arctic IDE on your development system by downloading and running the installer package. If you already installed the Arctic IDE for one Arctic module type, you do not need to install it again. Upon launching the installer, you will be presented with the Arctic IDE license agreement. Read it and accept to proceed. Then you specify the location, the installation directory for the IDE, using browse or accept the default directory location. Ensure that there are no spaces in the directory path name. Then click Next to proceed. The installer will display the installation location. If there's no further change, just click to install the IDE tools. The installation can take as little as 5 minutes, but may take longer, depending on the system. Click Finish to complete the procedure. On the initial run, the IDE will ask you to install the software development kit of interest corresponding to the devices you plan to use. Simply check the boxes next to the releases you want to install, typically just the newest. Also check the boxes next to the tool chains. Each time you want to open the Arctic IDE, locate and run the installed Arctic IDE program. Your interaction with the board takes place through a terminal emulator window. The Arctic Starter Kit communicates through an FTDI USB to serial device that requires installation of an FTDI driver. The following table shows possible terminal emulators and USB serial communication devices for each PC. You'll need to determine the COM port number assigned to your board. Start with the USB cable unattached, then watch the device manager to see which device appears when you plug it in. Check the COM port number when you connect a USB serial cable to the PC. If the COM port connection is not detected, you may need to power on the Arctic board. With the Arctic IDE installed and running, you will need to set up the COM port in its terminal emulator application. Open a serial terminal emulator console as follows. Start Windows, Show View, Console to open the console view in the lower right part of the IDE. Create a new command shell console by clicking the drop-down icon as shown. Then select the connection type to serial port. Create a new connection name with the options as shown below. Specify the correct COM port. When you reset the board, you should see boot messages on the console view. Log into your Arctic board if needed. You'll need to run through these steps each time you want to open the console for use. Open a console view by selecting Windows, Show View, Console. Create a new command shell console and select a port using the connector name you set up previously. Use the pull-down icon shown to select among multiple Eclipse console views. build and load status, debug tool, serial interface to your Arctic board. Create multiple console windows by opening a new command shell console and dragging its tab to a position elsewhere on the screen. Windows users may optionally install and configure PuTTY, P-U-T-T-Y, a free serial console program. Download PuTTY and install it according to the following instructions. Set the PuTTY configuration as follows. From next time, you can just double-click on the saved session name. Click Open. Initially, the resulting screen will be blank. Reset the board using the power push button switch. The Arctic module will now go through the boot sequence. When prompted to log in, enter root as the login name and root as the password. You should see something like this as shown on the right part of the screen. Here are some useful references for you to learn more about Arctic 710. Now, I'd like to take your attention to the Samsung IoT training YouTube videos. There are 10 of them. It may be very useful to take time and watch these videos. It may solve many of the problems or frustrations that you may have on getting it connected and using the Arctic 710 board. In the next lecture, we'll have some tutorials on hands-on experience with the Arctic module. Hello everyone, it's time for Arctic tutorials. This and the next tutorial will allow you to get hands-on experience with the Arctic board and IDE, Linux, and some programming. Arctic Tutorials website provides several useful examples of implementing key functionality with Arctic. We'll start by letting you use Arctic to record and play using Linux commands. The first exercise involves saying hello using the board. You can follow step-by-step instructions given in the Say Hello tutorials website. That is given on this website. Hi, welcome back. I hope you had fun with tutorial 1. I hope you had no problem following the tutorial guideline explained in the developer website. This is a second tutorial on Arctic. Having tried out some basic commands on your Arctic developer board, I hope you will naturally want to start programming next. In this tutorial, you will do the IoT universe's equivalent of the famous Hello World program. That is to use Arctic to blink an LED. You can follow the step-by-step instructions given in the Blink and LED tutorial website. Before doing that, please take a moment to set up Wi-Fi network connectivity for your Arctic board.